So, good evening, everyone. And we are waiting for our first speaker, Dr. Ashutosh. So, I think he has a class, so he'll be joining soon. So, please kindly wait for a couple of minutes.
Good evening, sir. Sir, you are muted. Ashutosh, sir, I think I'm fine.
Yeah, you are audible.
Dr.
Am I
Ashutosh?
audible?
Yeah, you are audible.
Yes,
now.
sir. Yeah, you are.
Okay.
I'm getting echo.
Is it fine now?
Hello.
Ha,
Yeah, it
you
is
are
fine.
getting my voice, sir? It's
Yes,
fine
yes,
now.
yes.
Oh, shall I start?
Yeah.
Meghna, you can start. Huh?
Again,
Okay.
it's like sort of.
So, yeah, Dr. Ashutosh, welcome to third day of our, 5-day workshop. So you have, around 1 hour and then continuation with the question and answers. So, Meghna,
Yes, sir.
you can.
So, being a proud alumni of IIT Indore, I am happy to introduce sir. So, Dr. Ashutosh Pandpe is Assistant Professor at Department of Civil Engineering, IIT Indore. He possesses extensive knowledge and experience in various aspects of environmental engineering, particularly solid waste management, and with more, like he has a thorough knowledge regarding various aspects of environmental engineering, specifically in solid waste management, and has experience for more than 6 years of working in the CSIR NEERI Nagpur. He has published his work in peer-reviewed high-impact factor SCI index journals such as Bioresource Technology, Chemosphere, Environmental Geochemistry, and Health, Environmental Science and Pollution Research, Journal of Cleaner Production, Journal of Environmental Engineering and Science, and Journal of Environmental Management. He was also awarded with the Best Young Researcher Award 2019, that is for Late P.S. Dutt Memorial Award for research scholars by CSIR NEERI Nagpur. He is member of various prestigious professional societies, including Indian Geotechnical Society, International Society for Soil Mechanics and Geotechnical Engineering, the Biotech Research Society, India, and American Chemical Society. Also, currently, Dr. Manpe and his team are conducting a study on the waste management mechanism in Indore city and exploring the behavioral aspects and perspectives of journal public towards waste management. Indore city has been recognized as the cleanest city in India for 6 consecutive years, and Dr. Manpe and his team is aiming to enhance its waste management practices further. So thank you so much for providing me this opportunity to introduce you, sir, and you can proceed with your lecture.
Hello, am I audible?
Yes, sir, you are audible.
So thank you, Dr. Meghna, for such a nice introduction. Also, first of all, I would like to thank Professor Neelim Satyam for giving me opportunity to express my views on this platform. Also, I am grateful for to the institute and for conducting such activities so that maximum outreach is done and we get connected to numerous students, researchers, and fellow colleagues, fellow researchers all over the world. So today's topic on which I'll be presenting my views are like breaking the plastic cycle, geo-environmental perspectives on waste management. So this is the flow of my presentation. So the very first slide, which I would like to, grab your attention towards here.
Sorry, sir.
Hello.
Sir, please
Hello.
share your slides. Please share the slides.
Oh,
Slides are not shared. Yes, sir.
Okay. Yeah. Just a sec. Are my slides visible?
Sir, yes, sir. Now it's visible. Yes, sir. You can make it to full screen now.
Yeah. Is it visible now?
Yes, sir. It is visible. It is visible.
So perfect. Sorry for the inconveniences caused. So
Okay.
my topic for today's presentation is breaking the plastic cycle, geo-environmental perspectives on waste management. This will be the flow of my presentation. As you have already told the audience about my area of expertise, I specifically work in the domain of solid waste management, and I will be speaking a lot about plastic waste, and I will try to develop some link between plastic waste and our landfills, right? So the very first slide, I would like to grab your attention or take your attention toward my presentation here. You can see the cutting or the screenshot of the news from a daily. This is the news from like February 24. Yeah.
Sorry to interrupt again, sir. Sorry, sir. Please make it a full presentation mode. We are getting messages in chat box. Like full presentation mode. It is not in full presentation mode now.
Okay, is it? Because
the next slide is also shown with the present side. I'll share the picture with you if you want to.
Good.
Like it is, if you can make it full screen.
In Ashutosh, in display settings, I think you are seeing the two slides, that the presenter slide and the main slide. I think you need to swap to one.
okay.
Yeah, now it's good. Now it's good.
Okay,
Yeah.
I hope now it is better.
Yeah, now it's good.
Now it's fine.
Yeah.
Thank you so
So
much.
these are the screenshots which I took or other clicks from the daily newspaper for Times of India. It is dated February 24, 2023 this year. And here I can, we can see the scenario of Indore, which we term as the cleanest city of our country, right? Still similar situations we can see, the fire in the landfills and the problem caused due to this. I'm unable to change my slide or what? I'm so sorry.
Slide is visible, sir. Are you able to change it?
Now this is another slide. Are my slides visible, Meghna?
Yes, it is visible.
Okay, now this is another slide. Showing the problem the fire caused in Kochi. And this is the news from the Times of India again, dated 13th of this month. Besides, I have another cutting like e-waste disposal likely to go up by 18%. This is the news from the yesterday's newspaper. Now, why I put such slides? Okay. So
Slides are not advancing, I think. Ashutosh.
sir, yes, sir. Sorry, sir.
The slides are
Hello.
not advancing. You are on the first slide, fire on trash mountains.
I'll just do it once again. Sorry for inconveniences caused again. Are my slides visible now? Again, the display settings.
Just put it in the presentation mode. And then now I'm seeing two slides. Yeah, swap that one to swap presenter view. And
So is it okay
slideshow.
now?
No, we're still seeing the two slides.
Now, fine.
Yeah.
Is it okay now?
Now it's good. Now it's good.
Perfect, perfect, perfect. So sorry, I mean, for the inconveniences to you people. I'm seriously sorry. I'm literally feeling nervous now. I mean,
no worries, no worries. It's good now. I think just see if you can advance it. See like 2-3 slides. See if you can go forward. See, can you forward the slides?
Yeah. So is it changing now?
Yeah, it's good. Yeah, now it's on contents. Yeah, go back to the first one. Yeah, that's fine.
Chalo, yeah. Perfect. Now I'll go to the first. This is the first slide again.
Yeah.
I mean, what we say, Indore being the cleanest city in our country, we still face the problems at landfills in Indore. This is the cutting from daily newspaper Times of India, dated February 24, last month. Another problem you can see from the Balaswa landfill in North Delhi. It is from the month April 2022. Likewise, you can see the image captured by satellite. You can say like of this Devna dumping ground, the landfill fires there. Besides, another toxic smoke to continue rising from Kochi landfill for a few more days. This is the news from Times of India, dated the 13th of this month. Yesterday itself, I found this news from Times of India, like e-waste disposal likely to go up to 18% in Indore, right? So the reason for showing these images or these news is that from this we should understand the gravity or the, what do you say, the problems we can face due to mismanagement of these plastics. Because as of now, though we have numerous technologies on paper, in reports, but on ground, there are very few which are operational and which are properly maintained. So the ultimate, what is the solution which is left for the waste manager is to dump these plastic as well as e-waste directly into the dump sites or in landfills. So this is the graph showing how much waste does India dump in landfills. It is in percentage. I took it from a CPCB report. Here we can see around 87% of waste is directly dumped in the landfills in the state of Odisha, while in the state of Madhya Pradesh, it is about in the range of 10%. I mean, this is from these numbers are from the report, I mean, provided by CPGB, Central Pollution Control Board. Now, how much waste does India treat? Another figures. It shows that Chhattisgarh is at its, having the maximum efficiency of treating its waste, that is around 85%, and the least, you can say is treated in Gujarat, right? Now, this slide is showing the number of dump sites which are present in our country, and spread across different states and union territories. So the maximum number of dump sites or landfills are present in the state of Uttar Pradesh, and the next number is of Madhya Pradesh, followed by Maharashtra. These are the actual clips from Devnar landfill, as well as other waste transfer station from Mumbai city. I had been a part of Brain Mumbai Municipal Corporation project while working at NIRI. So these are the clips from there. Now, exactly what happens when this waste is directly dumped in the open land or openly dumped? Like for example, we have example of trenching ground in our own city Indore, and which is adjoining that bio CNG plant, that Gobardhan plant, right? So exactly what happens when we dump around 1 ton of municipal solid waste, and that landfill is not having the facility of landfill like methane capture, then about 1610 kg of or CO2 equivalent gets, in the atmosphere. Besides, with the microbial degradation of this wet waste causes greenhouse gas emissions. Apart from that, there are fire hazards, odor problems, rodents and pests, and bird menace. There are many issues, right, in the adjoining areas, and gradually spreads all over there, right? So, as you might be aware about the infamous dump sites like Devnar in Mumbai, Bhawana, Bhalsua, Gazipur, Narela, and Okla in Delhi, Bingipura and Lakshmipura in Bengaluru, and Dhapa and Garden Ridge in Kolkata are a few examples of unscientific landfills in India. These dump sites are often in the news for the wrong reasons. Dump site fires were reported at Devnar in 2016 and again in 2018, which severely affected the air quality in the adjoining areas. In another incident at the Gazipur dump site in Delhi, 2 people died due to the collapse of 50 tons of garbage that came crashing down like a 16-story building, right? These are few of the environmental hazards, due to open dumping of waste. For example, surface landfill fire, and I have, bifurcated into 2 types: surface landfill fire and subsurface landfill fires. In surface landfill fire, if we go, if the facility accepts some, coal or like some barbecue coal, something like that, or overstuff the landfill gas collection system, a surface fire may ignite. Fires can also be started by arson, spontaneous combustion, or a dropped cigarette, right? Any person. Hello, am I audible? Hello, Meghna, am
Yeah,
I
you're
audible?
good.
Yes, sir.
You're
Audible.
good.
So I've bifurcated this, hazards into 2 types, like surface landfill fires and subsurface landfill fires. Assuming the audience, from UG, PG, and maybe fellow researchers, I will just try to explain in very simple terms what I understood, and the way at least just people should get aware about these things. So I'll just use the simple terminologies, or will try to explain in simple words. I hope my message reaches you people. Like there are 2 types of the fire may take place in the landfill by 2 types: on the surface, another one is subsurface. Fire can also be started by some spontaneous combustion on the surface, or as soon as the fire starts, it must be put out quickly to prevent more damage. The employment of heavy machinery to relocate the burning material to a safe location, the application of soil to put out the fire, and the use of suppression agents and firefighting techniques are only a few examples of possible actions in these cases. Apart from that, for subsurface landfill fire, spontaneous combustion or overdrawing a gas collecting system are the 2 main causes of subsurface fires. These flames are characterized by the fast oxidation of organic waste and tend to burn slowly without apparent flame or copious amounts of smoke. Besides, elevated temperature at the wellhead or the findings of soot in the gas collection system are used to identify subsurface fire in gas collecting systems. Likewise, if I would like to explain it in more simple manner, suppose if we are dumping waste, dearth of waste, that is heterogeneous type of waste, it is having organic, inorganic, everything, and we are directly dumping it in a landfill. So what will happen? In due course of time, sunshine hours, rainfall, moisture, everything will, act on it, due to which some reaction will take place there. So what happens when the layer of waste is, dumped one upon other, there are some gas packets which are formed, right, at the subsurface level, due to which, anaerobic digestion conditions are created there and methane gas is generated. So these are one of the major reasons due to which landfill fire takes place at subsurface level. Further, the other problems associated to dumping of waste at landfills are air pollution, dust particulates, water pollution. That water, what do you say? You might have heard about leachate. Leachate is nothing but the liquid that is very much concentrated in terms of contaminants, heavy metals. It gets percolated, right, in vertical direction, and it may get added to your groundwater recharge. So the people residing in the adjoining areas or in the vicinity of the landfill may get affected due by consumption of this water. Apart from that, epidemics generated by these degraded environmental components, and ultimately the soil in that area gets polluted. So process of landfill fire. The waste material is heated during spontaneous combustion by chemical oxidation and biological degradation. The substance reaches the point of ignition due to the heat that results. The degree of moisture present in the fill has a direct bearing on the type of fast oxidation that occurs in the municipal or construction waste site. Water is necessary for the biological decomposition of organic matter by the bacteria, both aerobic and anaerobic, which are present in it. In the presence of bacteria, organic matter and water react to produce increased heat, methane gas, carbon dioxide, as well as other gases. With the correct conditions present, spontaneous combustion can occur in household trash or at construction debris facilities. This type of combustion will produce excessive amount of carbon monoxide and other trace toxic gases due to incomplete oxidation. Besides, as I told you earlier, normally, barely we follow that segregation thing, source segregation thing, and even the, what do you say, the waste managers, there are different types who collect, they transfer the waste and ultimately they dispose of. They find their way easier for directly dumping the waste in the landfill, and this kind of activity is followed throughout the country. So ultimately, the mixed municipal solid waste gets dumped in the landfill, and the situation of leachate generation, air pollution, and other problems like soil pollution takes place at the landfill site. Now, plastics. Why I wanted to talk more about plastics in this situation? Wherever landfill site you find, wherever in India, you will find major portion of this inorganic part. These are ultimately carbon-carbon bond. However, these are the polymers, these are the complex, what you say, structures, which take a lot of years to decompose, right? Due to which they stay in the environment for longer duration. And in the case of fires, these are the major constituents which participate or rather which burn, right? Which create more problems. That's why I think we need to be more careful about this plastic waste. Since from last 50 years or from the time of independence, we have been dumping the waste directly in the landfill. And even today, similar practices are taking place all over the country. One cannot deny that this is not taking place or entire plastic is getting recycled, right? So as per the rules, the term plastic includes material composed of various elements such as carbon, hydrogen, oxygen, nitrogen, chlorine, and sulfur. These are macromolecules formed by polymerization and have ability to be shaped by the application of a reasonable amount of heat and pressure or any other form of force. It is one of few new chemical materials which pose an environmental problem. Polyethylene, polyvinyl chloride, polystyrene, and polypropylene are largely used in manufacturing of plastics. Plastic has a broad range of applications in packaging films, wrapping materials, shopping, and garbage bags, fluid containers, clothing, etc. What are different types of plastics? We can categorize into two types: thermoplastics, thermosets. Thermoplastics or thermosoftening plastics are plastics that soften on heating and can be molded into desired shape, such as PET, HDP, high density polyethylene, low density polypropylene. polyvinyl chloride, polystyrene, etc. Thermoset or thermosetting plastics strengthen on heating but cannot be remolded or recycled, such as sheet molding compounds, fiber reinforced plastic, bakelite, etc. are examples of thermosets. Okay. Now, once the plastic is discarded after its utility is over, it is known as plastic waste. And after this plastic in any form is littered or disposed of in the wrong manner, it becomes a major source of pollution in the environment. And this untreated bulk mass is termed as plastic waste. Example, in day-to-day life, we can see polyethylene bags littered on land, causes land pollution. As polyethylene takes a very long span of time to degrade, and due to this, land pollution leads to infertility of land. The waste quantities increased from 46 million tons in 2001 to 65 million tons in 2010. The report says that per capita per day production will increase to 0.7 kg, like 700 grams by 2050. On average, the production of plastic globally crosses 150 million tons per year. It is estimated that approximately 70% of plastic packaging products are converted into plastic waste into a short span of time. Approximately 9.4 million tons per annum plastic waste is generated in the country, which amounts to 26,000 tons per day. I mean, just imagine, I mean, as per a report of CPCB, I like giving such numbers. Assuming the current population of Indore, including urban suburb as well as some rural areas, the population is around 30 lakhs, 3 million. And as per the report by CPCB, the daily waste generation, that is municipal solid waste generation per capita per day, ranges between 0.4 to 0.9 kg. It varies with the, I mean, the localities, low income group, high income group, but on an average, even if we take just 500 grams or 0.5 kg of waste per capita per day, which comprises of everything: food waste, vegetable waste, paper, plastic, glass, everything. Just imagine 1,500 tons of waste getting generated every day on daily basis, and it is directly dumped in the dump sites, right? Apart from that, you just multiply the number per day. When I'm saying 1,500 tons, then multiplied by 30, I mean per month, and annually multiplied by 365. And the technology we have is like, those are on paper sort of thing, or they are acting on ground barely, right? It's like plastics are synthetic polymers derived from petrofossil feedstock and made up of long chain hydrocarbons with additives. The recycling of a virgin plastic material can be done 2-3 times only, because after every recycling, the plastic material deteriorates due to thermal pressure and its lifespan is reduced. Hence, recycling is not a safe and permanent solution for plastic waste disposal. It has been observed that the disposal of plastic waste is a serious concern due to improper collection and segregation system. Now, this slide shows the 7 types of plastics, right? The first one, polyethylene terephthalate, high density polyethylene, polyvinyl chloride, low density polyethylene, polypropylene, polystyrene, and even the years are given how long to decompose under perfect conditions. Like polyethylene terephthalate may take 5 to 10 years, while high density polyethylene will take around 100 years or maybe more, you know. Also, the low density polyethylene, it's showing in the range of 500 to 1,000 years. Just imagine, right? So ultimately, till the time it is present on Earth, it will just pollute the soil, the entire environment. Now, groundwater and soil pollution. Plastic is a material made to last forever, and due to the same chemical composition, plastic cannot biodegrade. It breaks down into smaller and smaller pieces, right? I have put some pictures from the, what do you say, ocean rather. We can see here the amount of waste which is there, maybe in that whale. So the plastics, when buried in a landfill, it lies untreated for years. In the process, toxic chemicals from plastics drain out and seep into groundwater, flowing downstream into lakes and rivers. The seeping of plastic also causes oil pollution and has now started resulting in presence of microplastics in soil. In recent years, like in last couple of years, more attention has been given towards microplastics, because the water even which we are drinking or the containers which we are using, those are made of polyethylene or plastic. Through that route, it goes in our body stream, right? In our bloodstream. And it will not be, what you say, a wrong comment. Even if we check blood sample of any human today, we will get some traces of microplastic in his or her blood. Now, harmful effects dangerous for human life. Burning of plastic result in the formation of a class of flame retardants. Collectively, these harmful chemicals are known to cause the following severe health problems like cancer, endometriosis, neurological damage, endocrine disruption, birth defects and child development disorders, reproductive damage, etc. Another thing, pollution in oceans. The increased presence of plastic on ocean surface has resulted in more serious problems. As you can see from this picture, since most of the plastic debris that reaches the ocean remains floating for years as it does not decompose quickly. It leads to the dropping of oxygen levels in the water, severely affecting the survival of marine species. Just for example, consider a situation, the home where we stay or where we live. We clean our home, right? And the waste which is produced or which is generated, we collect it and we put it in a dustbin, or rather just assume we throw it outside. We just think of keeping our home clean, but where does this waste goes ultimately? So these are the real pictures from where you can understand where this ultimately goes. There are different technologies, there are different things which are going on ground, they say. Unfortunately, most of the time such kind of waste is directly disposed of on landfills or are directly disposed of in ocean bodies. Now, a few numbers. Asia is the world leader in plastic pollution. The Philippines alone dumped over 1 billion pounds of plastics into our oceans. That is over 118,000 trucks worth. In 13 years, there is likely to be more plastic in our oceans than fishes. Just imagine. 83% of our drinking water contains plastic. Studies show that consuming plastic could lead to cancer, affects hormone levels, and heart damage. Plastics have been found in the blood of even newborn babies. Now, we will just have a glimpse of these things like persistent organic pollutants. Why we are talking about these now? Till now, we used to talk about like heavy metals which are present in the soil or any type of matrices, soil, waste, or water. But now, which one would have thought that these problems would have come in next 10 or 15 years? However, we can see the traces of these pollutants rather in terms of like ppb parts per billion, but these are present and these are gradually increasing and may come up in the range of part per million in just couple of years or maybe 5 years, next 5 years. So what are persistent organic pollutants? These are nothing but you can just understand an example of Teflon. You people might have heard about Teflon. Earlier, like around 5 or 10 years back, we used to get a Teflon coating on our vehicle, on our cars or on our bike. But nowadays we don't see that. The reason for that is this Teflon thing, this is made up of these persistent organic pollutants. These are specific kind of chemicals which have property of flame retardant. And as per the Stockholm Convention, these chemicals are termed as persistent organic pollutant. Why persistent organic pollutant? Because they will stay, or they are here on Earth, or rather they will stay here for more longer duration, right? The most commonly encountered persistent organic pollutants are organochlorine pesticides such as DDT, which we generally use in our agriculture sector, right? Industrial chemicals, polychlorinated biphenyls, as well as unintentional byproducts of many industrial processes, especially polychlorinated dibenzene. These are the current research areas where researchers are exploring various bioremediation techniques for dealing with these organic pollutants. These persistent organic pollutants are the chemicals of global concern due to their potential for long range transport. You might have heard about the grasshopper effect. These persistent organic pollutants are also found in the pristine environment where humans have not yet, visited there. Even in the Arctic, right? The presence of these pops can be seen. So these persistent organic pollutants have ability to biomagnify, bioaccumulate in ecosystems, as well as their significant negative effects on human health and the environment. Now, again, one of the major reasons increase in plastic waste generation is like 50% of plastic is discarded as waste after single use. Out of 60% of recycled plastic, 70% is recycled at registered facilities. 20% is recycled by unorganized sector, and 10% of the plastic is recycled at home. For example, the recycled by the registered parties or registered facilities is like they have the official authorized government registered authorized plastic recycling plants. 20% recycling is done by the unorganized sector, means the human scavengers which we see normally. I mean, in the landfills or nearby the garbage, I mean, dump area. These are human scavengers which ultimately help us to get rid of this problem. So the plastic and these, I mean, these are just part of, you can say, as a polyethylene, just for example, just for the sense of understanding. Humans are exposed to persistent organic pollutants in variety of ways, mainly through the food we eat and the air we breathe. It is said, I recently came across some report, it is said that whatever pollution we face in the outdoor environment, more than that pollution we face in our indoor environment. And thanks to these pollutants which we have at our home, like we have some polish on our wooden furniture, in the rugs, or the sofa or the couches what we use at our home, these all are covered with the layer of these persistent organic pollutants, right? Many products we use in our daily life used to contain and or may still contain persistent organic pollutants which have been added to improve product characteristics such as flame retardant or waterproofing. Generally, pollutants are accumulated at the source, but persistent organic pollutants can travel long distances by air and wind. They are found in environments around the globe, including close to industrial and urban settings, but also in remote locations, as I told you, in Arctic, high mountains, and the Pacific Ocean trenches, right? Also below the sea level, right? Persistent organic pollutants remain intact for a long time, are widely distributed throughout the environment, accumulate and magnify in living organisms to the food chain, and are toxic to both humans and wildlife. Why do POPs concern us? Scientific evidence shows that long-term exposure to certain compounds under certain conditions, even too low levels of POPs, can lead to increased cancer risk, reproductive disorders, alteration of the immune system, neurobehavioral impairment, endocrine disruption, genotoxicity, and increased birth defects. So the specific, what you say, the property of these persistent organic pollutants is that these are hydrophobic. These are not, I mean, dissolvable or in liquids or in water, you can say. They need specific solvents. Even for testing the concentration of these pollutants in any matrices like air, water, or soil is a very cumbersome task, because I mean, getting standards of these samples is also, those are very costly to develop the methods, because as I told you, these are in the range of ppb. You just need instruments like GCMS, MS, LCMS. Such type of sophisticated instruments are required. And what you say, mapping of these organic pollutants has not yet been done in our country. Another thing, there is no any specific law on these organic pollutants in our country. At the policy level, it is in discussion. However, there is no such law which has been enacted. Apart from that, in developed countries like US, or rather in major countries in Europe, they have banned the use of such chemicals. Under Stockholm Convention, every year these people put such chemicals in this category of persistent organic pollutants. However, there are specific chemicals like DDT and other chemicals which are essential for agriculture activities in terms of insecticides or fungicides, which are still in use, as well as which are being manufactured in India exclusively. We rather export these things to some selected countries, right, to enhance their agricultural productivity. So as we can see, these emissions, why I used earlier the word of e-waste, because e-waste also comprises of mostly of these persistent organic pollutants. Also, it comprises, it is mostly made up of plastic, as we can see. Just for example, if you think of burning a laptop, I mean, which is ultimately after its use, I mean, its useful life, it will be termed of as a waste. And if you burn, do you think will it burn directly? It does not burn, because it has such chemicals like these persistent organic pollutants, which are flame retardants, like polybrominated diphenyl ethers, right? They are one of the examples of this thing. then polychlorinated biphenyls, perfluoroactonic acid, perfluorooctane sulfonate, or right? It all are the part. This become the part of waste. As I told earlier, the mixed type of waste is dumped in the landfill. So ultimately, the person who comes in the, who gets exposed to such kind of waste in the landfill, directly felt prone to, these chemicals, and the results are like these are carcinogenic, and apart from that, as I told you earlier, this may result into like neurobehavioral impairment, endocrine disruption. Apart from that, as we can see in the dump yard waste, high density polyethylene, also from like electrical insulation, bottle, toys, possible POPs which may get released from that are PBD, polybromine diphenyl ether, PFAS, etc. Another like from dump yard waste, from biomedical waste, we may get container from low density polyethylene, film wrap, plastic bag, OCPs, PCDs, SCCPs, such kind of persistent organic pollutants may get released from this type of waste. Then e-waste, electronic waste, polystyrene, the plastic type which is being used there. Apart from that, its application in like toys, cabinets, packaging, coating for wiring cables in construction, as well as the possible persistent organic pollutants which may contain are polybromine diphenyl ethers, PFAS, etc. Now we saw some numbers about plastic waste, the persistent organic pollutants associated to it. Then we'll discuss a bit. I'll talk a bit about the laws pertaining to plastic waste. So earlier there was the municipal solid waste management rules 2000. Then new rules were framed like solid waste, municipal solid waste management rules, and exclusively there were the parts for plastic waste, electronic waste, biomedical waste, and so on. Now, salient features of plastic waste management rules 2016. These rules shall apply to every waste generator, local body, gram panchayat, manufacturer, importer, producer, and brand owner. Carry bags made of virgin or recycled plastic shall not be less than 50 microns in thickness. The provision of thickness shall not be applicable to carry bags made up of compostable plastic complying to ISO 17088. Then who are waste generators? Waste generators, including institutional generators and event organizers, shall not litter the plastic waste, shall segregate waste and hand over to an unauthorized agency, and shall pay the user fee as prescribed by urban local body and spot a fine in case of violation. Local bodies shall encourage the use of plastic waste for road construction or energy recovery, or waste to oil or co-processing in cement kilns, etc. It shall be responsible for the development and setting up of infrastructure for segregation, collection, storage, transportation, processing, and disposal of the plastic waste, either on its own or by engaging agencies or producers. Similarly, each urban local body, you can say right from Gram Panchayat till Nagar Parishad, municipal corporation, are endowed with some responsibilities for management of these waste, and they are abided by the rule like for performing the activities associated to like ensuring segregation, collection, storage, transportation of plastic waste, and channelization of the recyclable plastic waste fraction to recyclers having valid registration among all stakeholders about the responsibilities and ensuring that open burning of plastic waste does not take place. Producers, importers, and brand owners need to work out modalities for waste collection systems for collecting back the plastic waste within a period of 6 months in consumption within the local authority, state urban development department, and implement with 2 years thereafter. Concerned secretary in charge of urban development, body of state or union territory, and shall be authority for enforcement of the provision of plastic waste management rules. District magistrate or deputy commissioner shall provide assistance to state pollution control board or pollution control committee, secretary in charge, etc., whenever required for enforcement of provisions of plastic waste management rules. Then state pollution control board or pollution control committee shall be the authority for enforcement of the provisions of plastic waste management rules relating to registration, manufacture of plastic products, and multi-layered packaging, processing, and disposal of plastic waste. These are the major type of waste which are found. Now coming here to Indore, which is the cleanest city of our country. It has been awarded consecutively 6 times in the Swachh Bharat mission, I mean the Swachh Bharat Sarvekshan, which is conducted by the central government under the that mission of Swachh Bharat mission, Swachh Sarvekshan. The few points are given to several cities on the basis of how they manage their waste, right? So here Indore won 6 times consecutively. Now you can see this is a picture again, which I had shown you earlier. This is a picture from the city of Kochi in Kerala. The Kochi landfill site around Brahmapuram, Kerala, that recently caught fire is a stark reminder that Indian cities need to be prepared for more such incidents as summer approaches. Landfills are sites where waste materials are deposited, compacted, and covered with soil for long-term storage. These sites are designed to prevent contamination of the surrounding environment by isolating the waste from groundwater, surface water, and air. The openly disposed waste includes flammable material like low-quality plastic, which have a relatively higher calorific value and rags and flows. Higher temperature plus flammable material, it ultimately defines the chance for landfill to catch fire. Some fires have been known to go on for months. See, this is a picture from Kochi. The next, I mean, the clip which I had shared with you in the previous slide, in the starting itself, this is from Indore, which is the cleanest city, right? Indore, which says that garbage segregation is 100% and happens in 6 categories instead of just 2, wet and dry garbage. The bio-CNG plant that runs on the waste collected from the city is the focal point for the Indore Municipal Corporation's waste disposal procedure. In fact, it is not limited to CNG, but sewage from Indore is treated at 3 plants and converted into compost and construction activity material used in 200 public gardens and more, right? This is the, what is the positive part which one can, I mean, which one can think of, or rather which one can show on in news or anywhere. The negative part is that they say that the care is being taken of entire organic fraction of waste, but you will, I mean, it was difficult to digest that these people have no numbers, or they don't have any figures regarding how much amount of plastic is being generated on daily basis, or they don't have any number how it is collected or how it is disposed of. The only answer, after I had a discussion with this in the municipal corporation officials, I got to know that they have just given a firm called NEPRA the work of plastic waste management, where a person is not allowed to enter that facility, right? And that too, why it has been given to NEPRA, I will discuss in the coming slide. So another some positive things about this Indore city is waste generated from roadside food outlets is used to produce compost. The responsibility of waste composting is given to an NGO named Swaha, which is basically a startup by our own students from mechanical engineering department from our institute. And this organization uses a machine which is simple and easy to handle. For the processing of organic waste, a biomethane facility is provided which converts the organic waste into methane. This task is assigned to Mahindra Waste to Energy Solutions Limited. Then organic waste are processed to convert into biogas and manure. Now the waste generated, okay. The most preferred, what do you say, the waste management hierarchy is reduce, reuse, recycle, recover, and then dispose. I guess the people working in the domain of waste management or who are aware about this thing, the waste management hierarchy. Reduce at source, you should try to reduce the waste generation, right? Even if the discarded, I mean the waste generated, we should try to reuse it. We should try to get some measures so that how it can be reused. Further, it should be recycled. In the next stage, we should go for recovering some energy in the form of like, what do you say, biogas or something like that for organic waste. For inorganic waste like pyrolysis, incineration, you people can do. The least favored option, ultimately in the end, the least portion which is remained should be or can be disposed of in the land. Now, talking about this, reduce a few small steps in day-to-day life would help to keep plastic disposable plastic. Minimize buying bottled water. Minimize the use of plastic. It surprises me to know that, I mean, people are filing patent in Australia for making biodegradable plates using leaves. which is very much prominent, or rather which has been practiced in a rural areas in our country, like from quite long back, or maybe you can say around several decades, which have been used, which we are being using in our country. However, we are getting more attracted towards this fiber or plastic products nowadays, and people are tending towards these green products. Now, reusing a step up from recycling, it diverts plastics and takes the pressure off the recycling services. In fact, reuse is the middleman between reduce and recycle, and some would be surprised at how many opportunities for reuse there really are. One can reuse plastic produced bags for sandbags and reuse plastic silverware. Most people keep this safe and go directly to recycling, but reusing plastics can reduce the demand for new plastic to be recreated. You people might be aware in this recent, past couple of years, brands like Levi's, Spiker, or even Zara, they are looking after, utilizing, using this plastic waste and doing propaganda that they are using some green products, or they are just producing some lesser emissions, right? Sustainable manufacturing of clothes, they are focusing on that nowadays. Then recycling, benefits of recycling. Recycling and reutilization of waste plastic have several advantages. It leads to a reduction of the use of virgin materials and of the use of energy. There's also reduction of carbon dioxide emissions. Benefits of recycling, we know it reduces environmental pollution, energy savings up to 40 to 100 megajoules per kg. It has several economic benefits, reduces demand for virgin polymer, preferred to landfilling, generates employment, reduces depletion of fossil fuel reserves, etc. Right? Conservation of non-renewable fossil fuels. Plastic production uses 8% of the world's oil production, 4% as feedstock, and 4% during manufacturing process. It reduces consumption of energy, reduce amount of solid waste going to landfill, right? Then difficulties in recycling. It is hard to separate from non-plastic, like to magnetic equivalent. Differing composition of plastic resins means they are largely incompatible. Recycled polymer is of lower quality than virgin polymer. Identification of reuse and recycling opportunities, right? Market for plastics, lack of infrastructure, a low value of recovered plastics. In the next slide, we'll see recycling technologies like mechanical recycling. We can go for that. Feedstock recycling, plasma pyrolysis technology, plastic to road construction, right? Few CSR labs are working in this domain, as well as some IITs as well. They're looking after opportunities, or some small pellets they are developing, and they are using it for some construction activities, right? Besides plastic to fuel, one can go through this thing, pyrolytic conversion technology. There are several technologies of using plastics. However, the capex involved in establishing these facilities is quite huge. That's why people are a bit reluctant to go into this. Then recycling thing, application of recyclable plastics. As we can see, it can be used in apparel, as I gave example of Levi's, Zara, etc. PET bottle recycling system, used bottles, bottle belling, bottle sorting, then fiber is produced from that, and using that apparels are developed or manufactured. Another alternative is recovering the energy stored in residual material. That means turning waste into fuel for manufacturing processes or equipment designed to produce energy. Various mechanical, biological, and caloric systems and technologies can convert, reprocess, or break up waste into new materials or energy. Plastic to alternative fuel, the co-processing of plastic waste as alternative fuel and raw material in cement kiln and power plants. It can be used for combustion purposes in thermal power plants, in boilers, right? Then it can be used as co-substrate with some organic waste like dry grass or dry biomass. It can be clubbed with that, and briquettes can be formed. Then waste incineration. Waste incineration controlled burning is typically considered a disposal method because it is usually applied as a method of reducing the volume of miscellaneous municipal waste. However, incineration of plastic can also be seen as recovered method, as plastic could replace the application of other oil-based fuels. I've given some 10-step roadmap for governments to enact, for managing the problem of plastic waste. Target the most problematic single-use plastics. Consider the best actions to tackle the problem. Example, through regulatory, economic, awareness, and voluntary actions. assessing the potential social, economic, and environmental impact, spreading awareness among the common masses, identify and engage key stakeholder groups, retailer, consumer, industry, etc., raise public awareness, provide incentive to the industry by introducing tax rebates or other conditions to support its transition, use revenues collected from taxes or levies on single-use plastics to maximize the public good, enforce the measures chosen effectively by making sure that there is a clear allocation of roles and responsibilities, monitor and adjust the chosen measure if necessary, and update the public on progress. Promote alternatives before the ban on levy comes into force. The availability of alternative needs to be assessed. Hence, government may ensure that preconditions for their uptake in the market are in place, provide economic incentives to encourage the uptake of eco-friendly and fit for purpose alternatives that do not cause more harm. Support can include tax rebates, research and development fund, technology incubation, public-private partnerships, and support to projects that recycle single-use items and turn waste into a resource that can be used again. Reduce or abolish taxes on the import of materials used to make alternatives. Now, after 2016, government found there are still some loopholes or some lacuna is there. So it amended those rules, and significance of the new rules I have stated here. Category 1, rigid plastic packaging will be included under this category, right? Earlier, I have explained you the classification of plastic into 7 categories. Now they have sorted down to like 4 categories. In category 1, rigid plastic packaging will be included. Category 2, flexible plastic packaging of single layer or multi-layer, more than one layer, with different type of plastic sheets. Like we have pamphlets, right? Pamphlets are like plastic coated. These come under this category. Then plastic sachet or pouches, which will be included under this category, like shampoo pouches, etc. Multi-layered plastic packaging, at least one layer of plastic and at least one layer of material other than plastic will be included in this category, like huge posters, banner, right? Then plastic sheets or like used for packaging, as well as carry bags made of composite plastics fall under this category. Significant to develop new alternatives of plastic to reduce plastic pollution in the country, as the United Nations Development Program aims to triple the plastic waste management to 100 cities in India by 2024. To protect aquatic ecosystem also, as the plastic waste tend to end up oceans, soaking the life there. To invoke responsible behavior from citizens to change and contribute to waste management. It is one of the approach, circular economy. I mean, there are several approaches which have been introduced in the waste management sector, like life cycle assessment, circular economy. Such type of things are introduced just to make you aware about how much impact these problems are causing to the environment, and to rectify the issues, as well as finding some remedial solutions by following these techniques. Like a circular economy aims to eliminate waste, not just from recycling processes, but throughout the life cycle of products and packaging. A circular economy aims to maximize value and eliminate waste by improving the design of materials, products, and business models. Circular economy goes beyond recycling. The goal is not just to design for better ends of life recovery, but to minimize the use of raw materials and energy through a restorative system. In a circular economy, the value of products and materials is maintained for as long as possible. Waste is minimized and resources are kept within the economy when the product has reached the end of its life to be used again to create further value. Now here comes into the picture extended producer responsibility. Government thought of enforcing the laws of plastic waste management rules, which were framed in 2016. However, there were some loopholes or some gaps they identified, and they gave more stress on EPR now in the amendment, right? What do you mean by EPR? It is extended producer responsibility. It means the responsibility of a producer for the environmentally sound management of the product until the end of its life. Environmental compensation will be levied based upon polluter pays principle on non-fulfillment of EPR targets by producers, importers, and brand owners to protect and improve the quality of environmental and preventing, control, and abating environmental pollution. A committee constituted by Central Pollution Control Board under the chairmanship of CPCB chairman will recommend measures to Environment Ministry for effective implementation of EPR including landfill extended producer responsibility guidelines. State Pollution Control Board have been tasked to submit an annual report on extended producer responsibility portal concerning its fulfillment by producers, importers, and brand owners and plastic waste processors in the state, union territory to the Central Pollution Control Board. Now, in short, if you would like to explain, I'll just take more 5 minutes. It's 5:30 already. I'll just take 5 or 10 minutes. I hope, Dr. Meghna, it is not a problem. Hello.
Go ahead.
Yes, sir. Yes, sir. Go ahead.
Yeah. So, in short, if I would like to explain extended producer responsibility, in Indore city, like as I told you, they don't have any, the numbers or the amount of plastic which is being generated or collected or processed. They have given this responsibility to a private firm called NEPRA, and they are working under, I guess, in public-private partnership, maybe. So it is a responsibility. For example, if you understand any entity or any company which manufactures, plastic bottles or drinking water bottles, right? So these are the manufacturers or producers. These fall under this category. Just for example, XYZ brand is selling a water bottle. It is his responsibility because he is introducing ability to get back that plastic. It is also clearly mentioned in these rules that it is not necessary that he or she or a specific entity should recycle the entire plastic, but yes, it should look upon that and that the plastic which has been introduced by them, suppose 1 ton of plastic is introduced by them, so they have to take care that this 1 ton of plastic comes back, rather it is recycled or some appropriate measures are taken. So these companies tie up with these private firms and they get a certification or a certificate from them that this much amount, XYZ amount of plastic is collected and processed, and just the main company which produced that thing, it shows that certificate to the CPCB board, you can say, or any urban local body that they have taken care of the plastic. But ultimately, it looks good on the paper, but on ground you will not believe. Nobody knows what happens to that plastic. It is ultimately dumped or discarded in ocean bodies. Then the buyback depository mechanism, how it should work, it is explained. Then deposit return schemes operating in Germany, England, etc. suggest a model wherein the consumer has to pay an additional deposit as part of the price of the product, and the deposit is returned to the consumer on return of the product to the retailer. The consumers may also use the reverse vending machines which weigh and scan the plastic product to match against a list of acceptable shapes and sizes. If it matches the list, the product would go down a chute for either recycling or shredding, and the machine hands the consumer a voucher to be encashed at any of the stores. The machines could be located at strategic places such as malls, hotels, multiplexes, etc., and any other public places. As part of extended producer responsibility, the producers can sign agreements with retailers to return the plastic product packaging and received from the consumer for recycling purposes. The barcode on these products packaging may be used for tracking. Then for monitoring of this activity, a committee will be constituted at the central level for overall monitoring the implementation of the extended producer responsibility. The state level advisory boards constituted under Solid Waste Management Rules 2016 at the state level will manage the process of appraising the proposals submitted by urban local bodies and disbursement of funds to the ULBs, recyclers, and for this activity. Representative of producer, importer, and brand owners to be part of SLABs, state level advisory boards. Then again, similar committees can be formed at state level for monitoring purposes. The proposal of urban local bodies will be compulsorily for the management of plastic waste. Funds will be provided for a predefined set of items like weighing machines, baling units, etc. Such provisions are given in these rules. The monitoring mechanism will be established for the timely implementation of projects, allotment of predefined items to recyclers or assemblers. And the basic framework, the target will be assigned to producers based on the plastic put out by them in the market. As I gave you the example, producers will not be required to recycle their own plastics, but will be required to ensure that an equivalent amount of plastic is being recycled or reused. An instrument called plastic credit is proposed to be introduced, which is and will be evidence of recycling or recovery. Plastic credit will be issued by accredited processors in exchange for financial transactions to producers. Then the fund generated by the processors will incentivize the collection and segregation system and the recycling industries to increase capacity and capability to ensure the environmentally sound end of life management of plastic waste. Producers will be at liberty to engage individually or collectively with the ULBs, processors and the informal sector. The system aims to create a marketplace for plastic credits that can be traded, right? Again, now there are various perspectives. I mean, as I spoke a lot about plastic waste and the ultimate what is the destination of the plastic waste, according to me, is the landfill, which ultimately degrades the soil or pollutes the nearby environment, right? There are few technologies which can be adopted for proper management of this plastic waste. So like landfill mining, waste to energy recycling, upcycling. Landfill mining specifically will talk in terms of like legacy waste, which is present in our landfills. I guess this picture is a bit clear to you. MSW dump site, landfill mining excavation can be done. Accordingly, waste can be segregated, right? Like plastic waste can be segregated. If there is some organic fraction, it can be segregated. Soil can be segregated. Mining of dump sites may help achieve three broad objectives. It extend landfill capacity or free the land under the dump site for other uses. It yields scrap combustible fraction from scrap polymeric and combustible materials, yield inert fraction that can be used in construction and geotechnical applications. I had conducted one of such kind of study in the Nagpur city, where there's the Bhandewadi dump site is there. And I have also have some publication in ICE, Learning Journal of Environmental Engineering and Science, titled Mining for Recovery as an Option for Dump Site Rehabilitation, case study from Nagpur city. Nagpur is situated in the heart of like our country. The Bhandewadi dump site, which is, I mean, the Bhandewadi nearby residents of the frequent fires, contamination of groundwater, leachate percolation and greenhouse gas emission, triggering the climate change. The study which we conducted here, in this we considered two scenarios as a potential removal strategies, like mining for recovery. Another option we went for, like another scenario, transferring municipal solid waste from the dump to a new sanitary landfill. This study revealed that municipal solid waste mining for recovery was found to be more economical and sustainable compared to putting MSW into new sanitary landfill. This was the process adopted there. Landfill site data collection, including climatic, topographic, waste excavation, segregation into larger and finer fractions. Like larger fractions were sent to the recycling facilities, finer fraction application oriented tests like road construction, construction fill and others. Preliminary activities involved. There are historical analysis, waste sampling, installation of field test facilities, and waste classification, landfill characterization. We conduct that cost benefit analysis. Further, composition of Bhandewadi dump site waste at the surface at 2 meter depth and 4 meter depth. As we can see, waste composition at the surface comprise of around like 41% of plastic, while at 2 meter depth around 12% was there, while the inert was 75%, and at the 4 meter depth around 24% was plastic was present there, while 70% was inert. We did some cost benefit analysis. So for example, I mean, just to give a glimpse of that, out of the total area of 21.57 hectare of the old Bhandewadi landfill, an actual area of 17.8 hectare was being used for dumping waste. And assuming that average height of each debris is 5 meters, the total volume of waste that can be dumped was about 8,90,310 meter cube, assuming the average density of dumped municipal solid waste as 350 kg per meter cube. The total mass of municipal solid waste obtained can be around 31 lakh, what do you say, 3,11,608 tons. Also, Assuming 150 ton of waste processed per day, landfill mining of the entire landfill would take approximately 5 years. The estimated cost to be incurred for landfill mining is shown in the next table, where in the course of 5 years, it was found that the landfill mining will cost around 32 crores, 90 lakhs, like around 329 million rupees for over a 50 years duration. If we do landfill mining activity once in every 10 years, like 5 times if we do this activity, it will cost around 32 crore, 90 lakhs. In the next table, as we can consider this new scenario, if we go for new dump site in next 50 years, this is the cost it is assumed as per the guidelines given in CPHEO manual 2000 and 2016, and we have multiplied it with a factor of 2.520. Hello, am I audible?
Yes,
Yes,
you
sir.
are
Yes, sir.
Yeah.
Yes,
So average price which was considered was assumed was like $1 equal to 70 rupees. Today it is like around 181 or 82 rupees. So I just thought I'm just trying to show that if we go for this landfill mining practices, we can save like around what you say 57 lakh 24,600 dollars in 50 years, right? And this was the ultimate thing which I try to show there. I'll directly jump to the conclusion now. That study highlighted the importance of landfill mining and economic utilization in India due to scarcity of space for constructing new landfills in almost all cities throughout the country. The option of transferring municipal solid waste to new dump sites was found to be not economical and economically feasible in almost every city due to high cost involved. Mining of existing dump sites can be carried out to recover the inerts for their further utilization. This study showed that inert content was as high as 70% in MSW collected from 4-meter depth in Bhandebari dump site. Further studies like particle size, compression and shear strength analysis need to be carried out based on usage of the recovered inerts in civil engineering applications. While the cost analysis showed that landfill mining is one of the most sustainable, economical and technically feasible option in Indian cities for rehabilitation of existing dump sites. So with this, I'll stop here. Sorry, I took just 10 minutes more. Thank you for listening. Now I'm open for question and answers. Thank you.
Thank you so much, Dr. Ashutosh. I think it's a very interesting topic on landfill mining. So we are open for question and answer session. So participants, kindly either you can unmute yourself or like can put the question in the chat box.
Am I audible? I hope I am audible.
Yes, you are audible. And Dr. Ashutosh is very active dynamic faculty member in our department. So he's also a very active researcher looking for PhD students. If any interested, they can join his lab.
So I hope I did justice to the topic, sir, Professor Reddy. I hope I mean I tried my best.
No, your presentation is excellent. You covered a lot of different topics and a lot of interesting aspects. So yeah, it's very, very interesting to explore all the aspects that you presented.
Yeah, thank you for the kind words here. Thank you for your kind words, sir. Actually, in the starting, I was a bit disturbed then. I mean, how come that was happening? This different tools, Google Meet, then this thing. I mean, sorry for the inconvenience again in the beginning.
No worries, no worries. I think all the attendees are, our friends now.
That's great.
They have been listening to us for last 2 days, so they are kind and understanding. So anybody has any questions, you can ask Dr. Ashutosh. I think he has a lot of expertise from Indian context. He has worked on real projects in India.
Yeah, so
But
I'm just looking
anyway,
for opportunities. I mean, just like sort of blessings as well as some collaborations with people like you will help me enhance my abilities as well as my career perspective. I'll try to learn a lot if given opportunity with you.
yeah, you're doing good, Ashutosh. Keep it going. Don't slow down.
Perfect.
Yeah, so
Perfect.
it's good to
Perfect.
have some good PhD students working for you. So, as Professor Nilima mentioned, there should be a lot of students participating, and anybody who is interested in working should contact you.
So I'm looking forward to them. I mean, whosoever contact, let's see how I go. The present thing, I mean, the good part is that the situation, I mean, being in IIT Indore and Indore being the cleanest city, I had
Hmm.
been contacted with some consultant there in Indore Municipal Corporation as well as some, what you say, municipal commissioner, deputy commissioner. They are also
Hmm.
not aware about this problem concerning this
Hmm.
plastic waste because ultimately it goes
Hmm.
in the landfill and then it creates a problem there, burning issues, I mean like landfill fire issues and all. And even being the cleanest city, again I'm reiterating, they don't have facility about this thing, plastic waste management. So I don't understand, I mean, how these people are dealing that NEPRA firm. I will be soon having some, I mean, talk with them, some workshop with them. They have been inviting me to discuss on this topic. I hope something positive comes out.
It should be good, that you are in a indoor and people are looking indoor as a leader in doing new and innovative things. So you are in a right location.
Sure, sir.
So there is a lot of issues actually on landfill, management at the administration level. So actually, I was planning, to talk to the commissioner because I know him in some other forum. I met him. So he is also active, but still, like we could not make a proper discussions with them because they are looking with for a lot of help. I can say maybe because Ashutosh is already here and he can take your guidance even in future.
Yes.
So we can, maybe next visit of yours, we can think of some field visit so that we can have some kind of solution can be provided to them uh, from at least like institute side or from our department side.
Yeah, that
True,
sounds
true,
good.
ma'am.
Sounds good. So,
And even sir, mining also, that the Department of Mines is also having a lot of issues with the waste management, mine waste basically. So there is some consortia with Australia, Indo-Australia. I was part of that consortia. So there are a lot of other faculty from other IITs also involved. So we are also working on to do something. We have Professor Mohan from Australian team who is leading this group.
that's good. I think, the main issue is bringing all stakeholders and different expertise together and looking at strategies, holistic strategies to address the issues. So the problem is, I think, not having all the expertise at the table to discuss all the issues. I think, some people may have ideas on some things and they are not considering few other things, and other people have, other issues. What I feel is that there are multifaceted issues. You need to bring in people with different expertise to the table and discuss all these issues and take a action that addresses all the issues. I think now what I feel is addressing all this landfill waste issues in India is a little bit more fragmented, I think. I don't know, maybe
No,
just
true, sir.
looking
True,
from
true. In
looking
Indore,
from outside, I can,
true, true,
yeah.
sir. In Indore, what they have done is like they fill that landfill site with soil and they just planted randomly.
Yeah, I think that yeah, we could have more workshops, Dr. Ashutosh, in the future if you want to keep debating these issues. Probably doing online is less effort, but I think making people to talk loud, I think that would be the step forward.
True, sir. True, sir. My major intention, the primary intention was to highlight, at least give some glimpse of this persistent organic pollutants as well as EPR. Because for this EPR, I mean, huge economics is going, I mean, like anything. People are, I mean, flowing money like anything, like crores of money just for that certificate. And one has to point out the specific point where it is being done. I mean, officially can't say that, but sort of corruption kind of thing happening there. One has to look after that, because ultimately nothing is happening to the plastics. Those are dumped or they are discarded in the ocean. Apart from that, this persistent organic pollutants, because common masses or even the budding researchers, they should be aware of this, because they can think from that perspective as well for the research. So I just thought of putting some glimpse of that, and I think I tried to do justice with that topic. I don't know how come it reached to people, because
yeah, no, it's good. I think your presentation is going to be recorded so people can watch it, you know, if they skip some information, that will be good.
So
Can we move on to any questions? There is just a compliment saying that excellent exposition,
Discussion,
study.
collaborations, etc.
Yeah.
So if there are no questions, I saw one message in chat box. Of course, that was not the question. So feedback form, it's not actually the feedback form. Don't consider that as a feedback form. So it is just basically, if you have any queries on the previous sessions also, the last 2 days also, you can just post it there, and I would like to compile it and share it with all the speakers, and based on our time and something else, we can, have 1 more hour of discussions later based on the time of all the speakers available. So that is just to give the, if you have any thoughts or to share or anything, questions, anything for collaborations, you can directly post it there so that I can compile it and send across to all the speakers and the participants also. So that is one point I have. So with this, we are closing the first lecture. So thank you so much, Dr. Ashutosh, for the wonderful presentation. So second thing is like now.
Are you going to hang around, Ashutosh?
Yeah.
Okay. Okay.
So now, like we have a second talk from Professor Krishna Reddy, sir. Sir, it's all yours.
Yeah. So what I want to do is, today I'm going to present on a different topic on landfill gas emissions. And then it is one of our project, and we published several papers on this one. So what I want to do is, I want to provide you the link where you can find all the publications. And let me put it in the chat box before I start my presentation. So here is the link to the presentation, to the papers. I'm going to refer some of the papers in my presentation, so at least you know where to get those presentations. So let me share my screen and see if you can you confirm if you can see my screen in full screen mode and you can hear me well, Nilima?
Yes, sir.
Is everything is good?
Yes, sir. Just put it. Yes, sir.
Fine,
Sir.
Okay. Excellent. So again, this is the topic, sustainable biogeochemical cover for zero emissions at landfills. So at landfills, the biggest issue is the gas emissions and the leachate. So those are the two biggest problems in terms of environmental issues. So I'm going to talk about, the issues related to gas emissions. Remember, I mentioned this one in my first lecture. I work on environmental remediation of soil, sediments, groundwater, and stormwater. So, and then I also work on waste management and landfill engineering, sustainability and resilient engineering, and geotechnical engineering. So during my first lecture, I talked about one of our research projects dealing with electrokinetic and electrochemical remediation technology. And then yesterday, I talked about nanoparticles, how we could use those in remediation technologies. So I said I'm going to cover two topics related to environmental remediation. I can talk about other topics in remediation, but I want to give you kind of a broad perspective of geoenvironmental practices for environmental protection. So today I want to move on to this topic of waste management and landfill engineering. And specifically, I'm going to talk about one of our projects, biocovers. So, and then tomorrow I'm going to talk about bioreactor landfills. And then last day, I'm going to talk about sustainable and resilient engineering. That's kind of a remaining agenda. So before I get started, I want to thank all my graduate research assistants who worked on this topic over the years. And the one you see in the picture is Jyoti Chetri. She graduated last year, and she is now working as a project engineer in a consulting company in Houston, USA. And Dennis Grubb is my industry partner, Stefan Green. We did a lot of microbial analysis in this project. So we have a collaborator who has tremendous experience in analyzing and characterizing and analyzing the microbial data. So the funding for this project is received from U.S. National Science Foundation and industrial partner Phoenix Services. So in the presentation outline, I'm going to talk about what is this research problem. And so that needs to be said for every project that you're working on. You need to have a good understanding of what is the problem that real world problem that you're trying to solve, and how you propose to resolve that problem. That's kind of a thing. And I'm going to introduce you to a cover system that can address the landfill gases issues. And I'm going to detail all the research methodologies and results that we got, and then closing comments. So just warn you, research methodology and results, I'm going to give a brief overview to those, and then I'm going to show you the paid publications in which you can find a lot of details. So what we are talking about, as Dr. Ashutosh talked about, we're talking about the solid waste issues. It's not an issue only in India, but it's a global issue. So if you look at how much solid waste that we generate, millions of tons per year, right? So you see, South Asia, North America, we generate huge quantities of the waste every year, and if you're not doing anything with this waste, and if you're improperly managing the waste, every year after a year, you're getting, millions of tons of waste. The problem is going to, grow tremendously rather than, having kind of a same level or decreasing the issues. So overall, if you look at it globally, so these are the predictions on how much solid waste is going to be generated. Billions of tons per year. 2030, 2.5 billions, and 2050 is going to be 3.4 billion. Of course, this is related to population increase and the way of living, right? Living style, lifestyle. So this is a problem. I mean, this is a tremendous amount of waste that needs to be managed globally. What are we doing in terms of waste management? So this is kind of revealing. So you look at this one, open dump. Open dump is this blue. You can look at South Asia. 75% is open dump. Only 4% is the landfill, right? So this red is the landfill. And see, composting is 16%, and only 5% is recycling, right? And you can look at Latin America, 26.8%, Middle East, 52.7%. So in North America, so you see there's a lot of places, the waste is just open dumped. And if you see North America, it's in the US, for example, we don't have open dumps. Most of our waste goes into engineered landfills. There are see, the term landfill and open dump are used interchangeably in India, but they are quite different. Landfills are engineered structures, whereas open dumps are just, you find a ground and then you just start dumping without any liner systems or any engineered protections. So there is a big contrast, in India versus in the US. So in India, we still have large amount of waste is being dumped in open dumps, and very little in engineered landfills. And in the US, we have a lot of engineered landfills, and we don't have dumps. Obviously, we realized in the long time ago in North America, we used to have open dumps before regulations came into picture. And at those sites, the soil is contaminated, groundwater is contaminated, and some of those sites are called Superfund sites, and the remediation of the soils and groundwater is going on for years and years. So obviously, having an open dump is absolutely not acceptable in US context, and that should be the case in everywhere that we are talking about. So these open dumps should not be allowed. So that's kind of a reality of what's going on. So what can be done? Okay. Of course, landfilling is not a first option. So we need to be looking at integrated waste management. So collection, sorting is the most important thing. And then materials recycling is another important thing. And then you look at the biological treatment. That's an important option. And thermal treatment is another option. And probably landfilling could be the last option. So, when we talk about what do we do with the waste? So we need all these things. The collection and sorting is not going to solve the problem. Materials recycling is not going to solve the problem. You probably need some biological treatment. You need probably some thermal treatment. And ultimately, you might need some landfilling. So, as I was saying, that people argue that, okay, thermal treatment is the way to get rid of all the waste. That's not true. Or composting the waste is, is old way of taking care of the waste. But that's not true either. So we have to embrace all these different options, and depending upon the situation, depending upon the country, depending upon the location, depending upon many other socio-economic factors, we need to have a combination of these options. And you have to use all of these in such a way that you don't have any issues of environmental contamination affecting the public health and the environment. So this should be the high level strategy on how to manage the waste. We are going to create the waste. Don't say that no waste is going to be the option. Not create the waste is the option. But no matter what we do, we're going to create the waste, and the waste needs to be handled in an integrated way. So that's kind of important. So in landfills, no matter what you do, landfills are needed. Okay. So for example, if I incinerate, I'm going to get a ash that needs to be disposed of in a landfill because they will have a lot of heavy metals in them. So the landfills are engineered structures. So basically, sometimes you dig below the ground to the depth that is possible, and or you can have right near the surface if the groundwater is very shallow. But anyway, most of the times in the US, we dig down into the ground to the depth that is feasible. And then we put a bottom liner. Bottom liner consists of a composite liner. So basically you will have a compacted clay at the bottom. And then on the top of the compacted clay, you're going to have a geomembrane. Geomembrane is a plastic sheet. So this is the minimum that is required. Compacted clay that has the permeability 10 to the power of minus 7 centimeter per second. And the minimum thickness is 2 feet. So this is from USCPA, and many other countries follow the same guidelines. So the clay, compacted soil should have 2 feet thickness minimum, and K hydraulic conductivity should be 10 to the power minus 7. On the top of it, you should have a flexible membrane liner. Generally, it is 60 mil HDPE. That's kind of a standard, and that's always used for landfills. On the top of the landfill liner, you have to have a leachate collection system. So when you put the waste, the waste could degrade and create liquid that comes here. Or, before you put the final cover, when it is raining, all the rainwater will pass through the waste, and then that comes to the bottom of the landfill. So you don't want accumulation of that leachate. We call it that one as a leachate because the leachate has a lot of chemicals in there. So we don't want that one to accumulate. When it accumulates, basically you're going to increase the hydraulic gradient, and it's going to drive, and you're going to have excessive seepage through the liner, because you cannot say this is impermeable liner. So always it's a low permeable liner. So the regulation is that you cannot have more than 1 foot of leachate head anytime. So you need to have a leachate collection system. So you're going to collect it and remove it, and then you treat it on site or off site uh, to make sure that the leachate is handled properly. And then you put the waste inside, and then once you fill it up the waste, they basically put it in layers. And then once you fill it up, you're going to have a final cover. In the final cover also, you're going to have a compacted clay at the bottom, and then you're going to have a HDPE geomembrane on the top. So this is also minimum requirement, just like in the bottom, how you have. So here also you have to have that one, and then sometimes you have a drainage layer, sometimes you don't, but then you have a vegetative layer on the top. So this is engineered landfill. So bottom liner system, leachate collection and removal system, and final cover system. Those are the major engineered components in a landfill landfill. So the design of landfills is not a new thing, and a lot of these procedures have been established. So, for example, if you look at my book in section 3, so I describe how these components can be designed. So the section 3 starts with chapter 15 in the book. So it's 15 deals with sources and characteristics of the waste, and 16 about landfill regulations, siting and configuration. There is waste liner systems, leachate collection and removal systems, final cover systems, gas generation, groundwater monitoring, surface impoundments, beneficial use of waste materials, recycling, end use of closed landfills, bioreactor landfills. So I have the numbers that you see. They are not sequentially given: 15, 16, 17, 18, 19, 20, 23, 24, 25. So you have those numbers. And what I do is I teach a course on design of landfills and impoundments, a graduate level course. And essentially, I cover these topics in this sequence. It's very important, basically, I see like many universities teach a course on landfills, but they don't teach in a logical way, and the students get confused. If you start talking about landfill liners in the first class, the students get lost. So you really need to cover the topics in a logical way. So, what are we talking about? The waste characteristics, and what are the regulations? How do we locate those landfills? What are the requirements? What are the regulations? What kind of liner systems? So you have to go through logically in order to make the students understand it. So if you are interested in working on landfills or teaching a course on landfills, I highly recommend you to get hold of these books and look at these chapters, and you are ready to teach a course, or you are ready to understand all the aspects involved in the landfills. So that's the that's what we do it. We have a lot of landfills that have been designed in USA, and they have been monitored for many decades. And the landfills as designed are working fine. So there is no contamination of the groundwater. So that's why it is known as a well-established field. A lot of consultants to do the design, and a lot of industry people own landfills, and they own and operate the landfills. It's a kind of a good business in US for some waste companies. Now, let me just get a little bit more details into the waste management in the USA. So here you see how the total waste is generated in the US and what we are doing with it. Okay, so there's some amount of recycling, some composting, and some combustion with energy recovery. So incinerators, a lot of incinerators are shutting down in the US. So we're not using this a lot of we don't have any incinerators or waste to energy plants, so-called, and the ones which we have are being shut down. So most of the waste is going to the landfills, engineered landfills, not the dumps. Okay, so there should be some other food management strategies, composting. So as you see, so ideally you want to be in this waste management hierarchy: source reduction, reuse, recycling, composting, treatment, and disposal. Even though that is the hierarchy, but eventually in the US, the most of the waste is more than 50% of the waste is going to the landfills, and combustion and composting, recycling, and others. So this is the reality. You need to keep in mind, every country is different. In US, we have a lot of land, and most of these landfills are located way away from the cities, very far away from the cities where nobody is around. And they have a big landfills. These are large areas, sometimes 100, 200, 300 acres area, and they can last for 15 years, 20 years. So, waste is taken from the cities. And of course, you have a recycling at the source, and then you have some of the recycled materials goes there, and the ones which are not recycled, they go to the landfill, and they are transported in trucks. They go to the transfer station, and then from there in a big truck they go to the landfill and dispose it off. So it's good. Everything is good. But if you think about, the landfill leachate is managed by the leachate collection system at the bottom. Now let's look at the gases. So municipal solid waste has a lot of organics in it, and you put a cover on it. It becomes anaerobic conditions, and you have methane, CO2, and H2S, and some non-methane organic compounds are going to be generated as a result of degradation of the waste. Now, what happens if you don't have any cover, like dump sites you have in India? If the waste is getting degraded, all the gases are going out. Let's say you want to be a little bit cautious, and then you put some layer of soil on the top of it, right? But still, this contamination, these gases can diffuse out of the soil cover, and you're talking about a lot of gases, and you could have a pressure difference and concentration difference, advection, diffusion, all those things would be driving a lot of into the atmosphere. So even engineered landfills, like in the US, we have all the engineered landfills, right? So the bottom line are drainage collection system, and then we have a gas extraction well. So you put the gas extraction wells, and you apply the vacuum, and you try to collect that gases, and then you can use that for energy recovery or flaring. Obviously, you want to make good use of the methane that you generate for perhaps for energy production, right? So you have these wells, and then you extract it, and then you take it out. The problem with these extraction wells is they are generally very far away. They are located very far away. And depending upon the applied vacuum, there is the radius of influence, right? There's a radius. So within that radius of influence, you can, suck up the gases. So from that, you can get the gases, and you can take it out. And you get from here, within the radius of influence, you can get the gases, sucked into the well, and then, taken out. So you can do that. What happens in these areas, not influenced by the radius of influence? What happens to those gases that are there in that? So they basically come close to the surface, and then from surface, it's going to get into the atmosphere. So this is the problem. Of course, if you have dump sites, you're emitting everything into the atmosphere, which is really bad. If you have an abandoned site, if you have put a simple soil cover, that's bad. And if you have an engineered cover, that's also still not enough. And these, we have an engineered cover, but still we are getting these gases. So these gases are, that's why they are known as fugitive gases. These are the gases that are escaping our engineered design. What is the problem with these gases? So methane, CO2, H2S, and non-methane organic compounds. So methane and CO2 are greenhouse gases. As you know, everybody these days talking about climate change and extreme climate impacts. And that is because of methane and CO2. These are the greenhouse gases. And methane is more potent than CO2. If CO2, global warming potential is 1, global warming potential of methane is 28 to 36. So even, small amount of methane is having a huge global warming impact. And of course, the trapped methane is a, a real reason for fire hazards. All the fires that you see, that is because of methane. So H2S is other problems. It's methane and CO2, they don't smell anything. But H2S, even generally you have very small amounts, but they smell so bad. And if the landfills are closer to any people, and they're going to complain like hell. The smell when you go to a landfill site, methane and CO2 don't give you any smell. H2S is the one that gives you smell. So that means, you have this H2S is a problem. It's a corrosive and extremely hazardous, and also the odors are a big problem. And you can have a non-methane organic compound. So there could be hazardous air pollutants, kind of something could cause a cancer, for example, TCE, and because what is going into the waste? If you don't have a control on what kind of waste is going into the landfill, and if you live close to the landfill dump sites, you may be exposed to this highly toxic volatile organic compounds such as vinyl chloride, TCE and benzene, all those things. So this is why we need to worry about the gas emissions. We need to control these things. We should not allow these to be emitted. One, for controlling the greenhouse gases and resulting climate change, and the other one is from health and safety point of view. So if you look at in the US, I'm looking at in the US, the municipal solid waste landfills emit quite a bit of greenhouse gases, 89.2 million metric tons in 2018. And then, this waste industry in general emits a lot of CO2 and a lot of methane. So this is considered as the third largest source of greenhouse gas emissions. So if I want to do something for decarbonization or climate mitigation, I need to stop these gas emissions from the landfill going into the atmosphere. So what are the regulations on the cover? So basically the cover is the one that is doing the job, right, in terms of controlling the gases. So if you look at in the US, and probably same thing is adopted by many countries. I think Central Pollution Control Board also has the similar requirements in India. So you have a waste, some layer of a soil or selected waste has to be put as a foundation layer. So bottom main thing is you need to have a clay liner or soil barrier with a 10 to the power minus 5 centimeter per second. And the thickness has to be greater than or equal to 45 centimeters. And then on the top, 15 centimeter of erosion layer. So this is, important because I told you that you need to have a geomembrane on the top, but you don't have to have a geomembrane if the bottom is unlined. If the bottom has the composite liner, you have to have a composite liner on the top. But if you don't have a composite liner at the bottom, you can have just a soil layers. So this is what I'm saying. If you have a bottom liner, if you have a geomembrane, so the clay barrier, and then you have to add the geomembrane here. So same thing, but the geomembrane has to be added, and you have a vegetated layer. So from the regulatory point of view, this is the minimum requirements. So it's mainly designed to limit the infiltration of precipitation. So the idea is, 10 to the power -7, -5, or 10 to the power -5, and the geomembrane. So if you have that one, so when it rains, you're not allowing the water to get through it. Sometimes you will have a drainage layer between the vegetative, the erosion layer and the infiltration layer to allow any infiltration to drain off sideways. So the whole idea of this cover is not allow any water to get through it. However, in developing these minimum requirements, they didn't consider the fugitive gas emissions. The gases were not considered. They assumed that gas extraction wells will take out all the gases. But there is overwhelming data that shows that gas extraction wells that you have at the sites, at most their efficiency is 75%. So it's less than 75%. So you have 25% of the gases that are going to be fugitive gases. And if that extraction well system is not designed, it could be much, much higher, right? Also, people have looked at, hey, why do we need to have, the prescriptive cover? Can we think about something out of the box? So there are alternative covers. This is ET cover is called evapotranspirative cover. In some places, in US, it does not rain too much. So why do you need a, highly low permeable material, right? So you can probably use the vegetation to store and, evaporate the stored water. The capillary barrier is another concept where you store, you have a vegetative cover, fine grained soil on the top and the coarse grained soil on the bottom, and you create the capillary effect, and then water is going to be stored, and then it's going to be evaporated or evapotranspiration happens, that gets removed into the atmosphere. Other one is the engineered turf. The nowadays, people come with a soil, and there's a geomembrane on the top of it is a turf, artificial turf that can be placed on the top of the waste. So you can look at this reference, advancements in municipal solid waste landfill cover systems, a review for getting an idea about all these different cover options. So recently, there's a new concept, a new cover system called BioCover has come into existence. What is the BioCover is that, you have a waste at the bottom, and you have a cover here. It could be entire cover or maybe part of the cover where you put a gas distribution layer, and then you have a material here. You put an organic material. So soil, it could be amended with some organic material, and that organic material could be compost or peat. And what happens is, with that situation, you have some kind of the bacteria, microbes, mainly methanotrophs, that oxidize the methane into CO2. So instead of methane coming out, methane gets converted into CO2, and CO2 comes out. CO2 is less global warming potential, like a 1, and whereas methane is 28 times. So if you convert, 1 methane, that means you are, reducing the 28 CO2s. So that's the whole purpose of this one. So you could have a low permeable layers outside. These are called windows, or you could have an entire layer as this material. So the whole idea is methane and CO2 is coming into this layer, and in this one, microbially, you are oxidizing the methane into CO2, and then CO2 is coming out. Now, these materials that you see, compost and peat, these, they are not stable materials. So if a compost is not matured enough, the degradation of that will generate the methane, more methane. So when you add compost into the soil and they put this one, you're creating the more methane. And they could degrade with time. So there are issues with this one. So these covers, as I mentioned, ET cover, capillary barrier, these are, designed mainly to minimize the infiltration, whereas this biocover is, okay, minimize the infiltration, also minimize the methane emissions. And then because we have these problems, compost and peat, they're not stable materials, and we thought about it, can we use the biochar, right? Can we use the biochar as the organic amendment in the soil? Now the question is biochar. Many years ago when I started, nobody in knew in geotechnical or in landfill field what biochar was. So
Seems no one from the post, ma'am.
Hello? Yeah. Nikhil, are you there?
Yes, ma'am. I think some connection issue.
So I think some internet issues.
Yeah, some internet issue was there, ma'am. System was
Yes,
collapsed.
yes, I think.
That is there.
Okay, I think we are back. We are back.
sorry, something happened and it stopped working. So anyway, so let me share again. All right. So it was okay, right? Until this. It was good?
Sir, it's fine.
Okay.
Yes, yes.
So the pyrolysis and gas, I don't know what happened. I just kicked out of the Zoom. So here, pyrolysis and gasification, these are the units in which you burn the biomass without, having too much oxygen in it. So these guys are mostly interested in producing the bio-oils, biofuels, okay? But this process generates so-called this biochar as the waste or byproduct. Okay, they didn't care about that one. So they were mostly interested in this one. So this is the one because it's generating out of this biofuel production. Can we use that one? So depending upon what biomass that you're using, and then how you're burning it, and you can get different types of biochars. So I'm showing you the pictures of these different types of biochars, how they look. Okay, sometimes they come as pelleteds, the powders. So all these different forms that you get it. All right. So this biochar, people were basically taking it to the agricultural field and spreading on the ground, and they're seeing good agricultural production. This biochar has a lot of interesting properties. It has a high surface area, high internal porosity. It has a high water and nutrient retention capacity. It has highly resistant to biotic degradation. So as I said, like compost and all, they are not stable. And this biochar is known to be stable. Nobody knows how long it's going to last. The people say, it's going to last for many, 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 many years. And it can absorb the gases. So like if I'm trying to use for in the cover, it can absorb and make gases available for microbes. So if it is not absorbed, maybe gases may be escaping faster than microbes can oxidize. And then you can it enhance the microbial colonization. So microbial colonization is very important because this internal porosity is so nice that these microbes want to go there and reside and multiply. So that's kind of an interesting aspect of this biochars. So as I said, this biochar has been used in agriculture for soil quality improvement, carbon sequestration. And then I have also used for environmental remediation of soils and groundwater. And then we said, okay, why can't we use as a organic amendment in covers? So we were the first ones to propose for covers. One thing I want to mention to, if you are interested in knowing about which biochars to use, when you produce the biochars, you really need to look at are they environmentally friendly to use? Because depending upon the feedstock, depending upon the pyrolysis processes, you may have a contamination in there. So we got these commercial biochars from different sources, and we characterize them for the pHs and metals. And you can see some of them have high concentrations of pHs and metals, and some of them don't have it. So for example, this one is a below detection limit and metal concentrations are the lowest. So some other ones had the higher concentration. So one thing I would suggest is that whenever working with the biochars, I know people are more interested in thinking about their application, but first and foremost, any kind of waste material, any kind of byproduct you want to use for application, you need to characterize its leachability or chemical composition. That's the point that I wanted to make it. So we wanted to see, okay, is biochar is going to work. So we basically, what we did is a simple column experiment. So we filled with soil. One column is with the soil. Other one, we put a 20% of biochar mixed with the soil. And then we put that one and we injected this simulated methane, simulated gas, and simulated landfill gas. So landfill gas is generally, um, you know, uh, 50% methane, 50% CO2, but in this case we used 25% methane, 25% CO2. Rest is a nitrogen. So basically, we wanted to see is this methane, what happens to methane and CO2 as it coming through it. We have pores to kind of collect the samples and analyze them, and then we collect the gases that is coming out, and see what is the composition and also what is the flow rate. And then based on this depth below the surface, you can see oxidation efficiency of the methane. So this is the column 1. So you can see that the oxidation rate increases significantly, across the depth, with the depth up to certain depth, because these microbes need oxygen. So the maximum methane oxidation happens near the surface, and as you go deeper, it could be oxygen limited conditions, and then it may not be as efficient. But overall, you can see a lot of methane is oxidized in the column 2 with the biochar. And this is the paper that you can find a lot of details about it. So then, we said, okay, we're giving good results. Can we optimize the design, optimize the content? So we have a control with just the soil, and we looked at, okay, instead of putting the entire soil with the biochar amendment, can we reduce it? Because the more biochar you use it's going to be more expensive, more tedious. So we said 2% biochar here, and we said here 10% biochar. So we don't need across the entire cover, maybe some zone where we expect the maximum methane oxidation. So maybe we can put it in that. And in one case, we put 10% amended soil entire profile. And then again, like what I showed you in the previous slide, we would inject the simulated landfill gas from the bottom, and we look at what is happening along the depth. So you looking at these profiles. So you can see this is the cell 1. So the concentrations are high across the profile. But if you look at the last one, this is the 10% amended biochar, you can see the concentrations are very low because the methane is being oxidized. So clearly, we could show that the biochar amended soil will have a significant increase in methane oxidation. Okay, so those were kind of initial studies. Then we said, okay, this looks very promising. Let's do a lot of additional research to see if we can make cover that could be applied in the field. So we know that just using the soil covers, conventional covers, even with engineered landfill gas capture, they're not going to be effective. So we're going to have some fugitive gas emissions. And then based on the preliminary testing, we found out that biochar-based biocovers can oxidize the methane into CO2. But, that is like a solving problem partially. So if you convert a CH4 into CO2, that CO2 is still a bad thing. And then you have a lot of CO2 that is emitted that we are not considering. So how can we consider the CO2 that is coming from the waste, and then how do we consider this, the converted CH4 into CO2? So that's the problem. And you have H2S that gives you odors. How do we address that one? So how can we solve the problem of landfill odors and greenhouse gas emissions? And that way we can address the climate change issues and health hazards related to landfill gas. So we thought we need to kind of rethink about cover system and see if we can come up with some sustainable cover system to mitigate the landfill gas emissions. So our research goal was that. Research goal was to develop innovative, low-cost, practical, feasible, and sustainable cover system. Can we eliminate fugitive landfill gas emissions, especially methane, CO2, and H2S? So we call this one as a biogeochemical cover. So in this one, what we are looking at, the hypothesis is that biochar amended soil will mitigate methane emissions by microbial methane oxidation, as we proved with our initial experiments. And then what we want to do is we want to add the BOF slag on the top of it, so that the CO2 that is a methane conversion to CO2, that CO2 and additional CO2 coming from the waste and H2S coming from the waste, can we mitigate that one using the slag? So basically, we are trying to eliminate these three gases that are coming out. So idea is to eliminate these major gas emissions. So zero emission cover, you can call it, because we are trying to take out all the gas emissions that is coming out. So that's the kind of is a transformative approach to eliminate all the gases, and as a result, we can reduce the greenhouse gases and protect the public health. So how is this? This is the new idea, biogeochemical cover. How does it work? So basically, we are talking about the cover system being doing it differently. How are we going to do it? Let's look at that one. Okay. So here is the waste at the bottom, right? So the bottom, you have a waste and it's degrading it, and you have methane, CO2, and H2S is coming up. And then you are having a biochar amended soil. And in the biochar amended soil, you have a methanotrophs, right? And biochar will enhance the methanotrophs in terms of the quantity and activity. And then you will get enhanced methane oxidation. So that methane oxidation, CO2 comes through. So this CO2 comes up, and this CO2 from the waste comes up, and the H2S from the waste comes up to the slag layer. So we are proposing having a slag layer. In a slag layer, you are sequestering the CO2 as Ca calcium carbonate, and then H2S as iron sulfates. And then on the top of this, you're going to have a vegetative cover soil to put the plant. And this does not have to be any engineered soil. You can just put a soil that can support the vegetation. It could be permeable, and we want some water to infiltrate, because we want the slag layer to be a little bit wet. So that's our the whole concept of biogeochemical cover system is biochar amended soil and overlain by slag layer. The biochar is a byproduct of pyrolysis of the biomass, and the slag is also byproduct of steel manufacturing. So basically, we are using the byproducts or waste materials as a part of this. Now, okay, so let's look at this a little bit more. So we said, let's understand these, how they work. So this biochar amended soil, we try to do more investigation on it. So we did many batch tests, and we did also column experiments. So this is how batch experiments basically, you take these small glass bottles and then put the material and put the gas, seal it off and put the gas in there, and then collect the gas sample and see what is happening to the gases, right? So if methane is converting into CO2, that is reflected in the concentrations that you take the sample and measure it, how much is the methane and CO2, you can do that. And then these are the columns. These would simulate what would happen in a real column. So if you have a column, a cap, cover, So you have a distribution layer at the bottom, and the soil gas is coming up from bottom to top, and these are the ports that you can collect the gas samples and see at any time what is happening to the gas as it goes through the liner system. So we have multiple columns simulating the multiple scenarios of the cover. So the batch tests are easy. You can do many of these things to understand the fundamentals. So here, what we did is, okay, we took the soil and we did the testing. So you can see the soil with time, how methane uptake happens. So you can see the microbes are there and they keep on taking the methane. And then we did 2% biochar amended soil. So 2% with this, the open circles. You see that open circle, there is not much difference. And then after some time, you see that this deviation that happens. So basically, when you add 2% biochar amended soil, there will be a lag time for the methanotrophs to acclimate to the biochar that is present. So it will all this time where you don't see much difference, that's acclimation. After that, you see that the oxidation is higher than the soil. And then when you add more 10% biochar, again, you need time for the methanotrophs to acclimate, and after that you see it deviates. So you don't expect right away the methane oxidation to be increasing. So it will take some time for the methanotrophs to acclimate, and then you see this. So at the end, you see that listen, we are not really, this is not a short-term test. When you put the cover on it and we're going to walk away, that cover is going to be there for years and years. So if this happens initially for a few days, you may not have, for example, 60 days, you don't have anything happening. But after that, this one with the biochar, they are taking off with high methane oxidation. And of course, we did only up to 90 days or so. But if you don't want to have this lag time, you can actually, activate the biochar with methanotrophs. So you can create a methanotroph culture, and then you basically, spray it on biochar, and then use that one in the soil. So if you do that one, you already have, methanotrophs in the biochar system, and you see that there's no lag time. So this is a 2%, and this is a 10%. So tremendous increase in methane oxidation within the short period of time. So again, this convinces that this activation, it sounds good in the lab, but in the field, you cannot do it. You cannot like spray so much soil with this methanotroph solution. So I think resorting to this and allowing the acclimation time is the best option. So the column experiments are important, because in this one we are mixing everything. In the batch experiments, in the column experiments, gas is flowing through this column, and that's more close to the conditions. So we did the testing with the soil column, 2% biochar, 10% biochar, 10% biochar at different locations. And as you see from here, so the soil versus 10% biochar, there's a huge difference. So we concluded that the more the biochar, the better it is. And then we did also microbial characterization. So this is my student, she was extracting the DNA, and then we send it to DNA center in our university. They will do this analysis, and then they give us the information about different methanotrophs that are present. We're more interested in methanotrophs, total amount of methanotrophs, and the types of methanotrophs that are in there. And that kind of reveals, okay, you have the oxidation data, but which microbes are really doing the job. So then what we wanted to do is biochar amended soil can be used in the field or not, and how it will perform in the field. So we went to the field and we did the test plots. So in this case, you have an existing intermediate clay layer, a coarse gas, and then you have a 100% cover soil. This is like a baseline. And then we put the biochar, 2% biochar amended soil layer. And here we put a layer of biochar, and here we put a 10% amended biochar. So basically, we try to create different profiles in the field. And then how it is done is we go out to the field, basically go to a landfill. On the top of the landfill, you probably have an intermediate cover. We excavate out that existing intermediate cover, go to the top of the waste, and then these guys didn't allow us to go all the way to the waste, but we had to put 1 feet of soil on the waste, because they're worried about direct exposure of the waste to the atmosphere and giving a lot of odors, and people in the neighborhood complaining about it. So then we put a gas distribution layer, gravel at the bottom, and then we put either soil amended with the biochar, or the biochar layer thin layers amended. We just mix the biochar and the soil, and we found that it's easily mixable. Mixing is the biggest challenge. We could use the tilling equipment, conventional gardening equipment, to do all the work. And then we put the gas probes at different depths, and then you have these, see on the top you have with the port that you can use to collect the gas, and this at the bottom of these probes is at different depths, so you can see collect the gas samples. Like in the column, we collected at different depths, right? In the field, how do you do it? So you have these gas tubes extending to different depths, and then we collect the samples from different depths, and we can look at it. And this is how install test pads look like. So we have bunch of them, and we have replicates. So we have and the results in just showing the main results. So if you look at just the soil control, you can see the concentrations are higher. But if you have, let's say, 10% biochar, the concentrations are lower. So obviously, even under the field scenario, you can see significant decrease in the methane concentrations and CO2 concentrations. So there are a lot of publications. I put a link in the chat box, so you can download all these papers from my website. So that's a biochar amended soil. So that's good. So we are set. We proved it in the batch experiments. We proved it in the column experiments. We proved out in the field. We are now confident that biochar amended soil can actually do this microbial methane oxidation. So that's good. So now the challenge is to address that CO2 and then H2S. The slag layer is the one that we proposed. So you probably know, we call it a slag, steel slag, but there are different types of steel slags, right? So you can see, blast furnace slag, and you have a BOF slag and EAF slag, ladle slag. So, a lot of times the distinction is not made very clearly. Again, in this blast furnace slag, you could have these different types of slags. What we are looking at is the BOF slag. And why we picked the BOF slag? Because we have steel plants right next to Chicago, and they have this bigger size slag particles are used as a hard material for pavements. They are selling that one extensively. But the problem is that the finer material that they get out of this, as you see the piles of these in the back, that have no uses. So this, as I said, coarser material is used as a aggregate material, but these slag fines, they are commonly stockpiled. This is the steel plant close to the site. These are my students, and I was there. And right now, this fine slag is occupying the space at these plants. The only way to get rid of this one is to send it to a landfill. So they said, like, okay, we want to get rid of this one free. Okay. So can you find some users? So that's the particular type of slag that we are looking at it for this application. So, but we don't want to use the other type of slag because this has already good applications. That there's no point in dumping the useful material in the landfill. So we wanted to look at this slag fines, and then you characterize what are the properties of the BOF slag. Basic oxygen furnace, BOF is that one. So you need to be very clear with what type of steel slag that you're using. So specific gravity is obviously very high, and the pH is the one which is very high. Those are the kind of distinct properties of the slag. So again, we are using the waste materials or byproducts. So I always try to do a leachability study on that one. So are there any contaminants leaching? Because I don't want to cause, I'm trying to, address the environmental problem, but I don't want to create, new problem while addressing one problem. So that's why. So the gist of these results is that, we find the BF slag, contains some metals, but none of them are leachable, and it's considered as a non-hazardous. That's fine. Other important thing is to look at the mineralogy and the bulk chemistry. So oxide bases and minerals, you can see all these things. So what I'm showing you here is we got this BF slag from 3 different steel plants, IHE at different times, and Riverdale is another steel plant. So the main important thing is, we are trying to rely on some calcium. Uh, Slag is the source of calcium. So the main thing, and also iron to sequester the H2S. So the most important thing that you need to look at is, where the calcium is going to come from. The calcium oxide, lime, potentillite, and lernite. So you see which minerals that you have, and how much they have, and what is the potential for making calcium available from, or calcium or iron available from them. So then once you know that, you can, now the question is, can this slag take out the CO2 and H2S? Can it take out? So what we do is so we have these 3 different slags, and then we did the test at different moisture contents. One thing is highly revealing here is, if the slag is very dry, you will not get any sequestration. But if you have a 10%, 15%, 20%, you need to have some moisture. So this one with the 10% moisture content, this slag had very high carbon sequestration. So each one has a high amount of sequestration, but you need to have the moisture. So nothing happens to the methane. So mostly the CO2 is going to be sequestered. So even if you put a gas source that has the methane and CO2, the CO2 is the one that is going to be sequestered. So that's why I was telling you, you need to let some moisture from the top going into the cover. The column test, the small column test that we have done. So basically, you look at the concentrations of the CO2 and how much is coming out. So the percentage CO2 concentration with time. So you see that initially all of the CO2 is taken. This is the column experiment. So you're putting from the bottom, you're measuring on the top. Nothing comes on the top until you reach certain pore volumes. The significant number of pore volumes are needed for one of them. It's like 100 pore volumes are needed to see something coming out. So this is all total sequestration. And then it comes out, and then you see eventually inlet and outlet comes of the same. So based on that, you can calculate how much is the CO2 removal. And again, doing the testing, it shows that like look at this pattern. So you look at it closely, if you look at it, so it has a distinct slopes. So those are attributed to the different minerals providing the calcium. So initially you have one mineral providing the calcium easily, and after that you have another mineral that's providing slowly the calcium. So the rate of removal depends upon how the rate of release of calcium from these minerals. So that's kind of the interesting observations we found. So H2S sequestration is another important thing. Again, we put the slag and we put the H2S in there, and then see how much is getting removed. Again, we found out that extensive amount of H2S is removed by slag. So which is, very positive news for us. Our hypothesis is holding. Now, thing is, we looked at H2S alone, but H2S in combination with a CO2 and methane. So again, we show that CO2 is taken out and H2S is taken out. So both of them can be taken out at the same time. So that's kind of the interesting thing. And also what we found is this the slags, finer the better. So the last slide, the last graph that you see, H2S versus the coarser materials that you see it. So in fact, that is even better because we are trying to use the fine fraction of the slag anyway. So we are getting finer slag anyway. So these are the publications you can get see it and then get more information about it. Now, we looked at the biochar amended soil, we looked at the slag, right? But we want to use them in combination. So then we try to do these column experiments in combination with the biochar amended soil and the slag. So how we did it is we did it in a sequential order. So let's say we have the column, and we have different columns, the 4 columns. So in one thing, we initially we put the gas distribution layer. Basically, we put the gravel at the bottom. In one of them, we put the only soil. Other one is 10% biochar. This one is 5% activated biochar. Here is 10% activated biochar. We were trying to look at, how much is the optimum biochar amount and whether we should use activated or not activated. Okay, so that's kind of the idea that for designing these experiments. So basically, we have a distribution layer and this is the soil layer. Okay, and then later on we're going to put the slag on the top of it. But initially, we wanted to look at this biochar amended soil again in this type of configurations. So this shows the pictures of our columns in our lab. And then we have a monitors, moisture, temperature, and those are all connected to the computer. So remember, one of them here, we are talking about activated biochar. So this is how we created the activated biochar. So we got a landfill cover soil. We added this NMS media. We did the soil enrichment, and we separated and then we use that culture mixed with the biochar, and then that becomes the activated biochar. That's the methodology that we used to create that activated biochar. And then we got the results. So we basically run in different phases: phase 1, phase 2, phase 3A, phase 3B. So first stage is acclimation stage. Second stage is we expose it to the mixed landfill gas, and then we can simulate whatever we want. So in the 3A, we just put in methane alone. And then in the 3B, we exposed pure methane after addition of the sand on the top. So, we try to kind of design different phases of the testing to look at, understand what is happening under different gas conditions. And then in each of these tests, we do the microbial characterization. And microbial characterization is done similar to the procedure that I mentioned before. So we take out the soil sample, we do the DNA extraction and the qPCR application of 16 sRNA genes, next generation sequencing, and then all the taxonomic classifications, and then comparing the relative abundance. And then mainly we are looking at methane oxidation, methane oxidizing bacteria. So I'm not going to go a lot of details about this one. So you can find a lot of papers. So at different stages, stage 1, stage 2, stage 3, in the column experiments, you can see how much of the methane oxidation is. Stage 1 is the acclimation. Initially, you don't have methanotroph, so the oxidation efficiency is low. And stage 2, stage 3, you see the oxidation rates have gone up. And that is also clear from the gas profiles you see here. CO2, CH4, the ratio of them was at the inlet is 1. And then if you see the ratio is more than 2, 3, that means what? You know, most of the methane is converting into CO2. CO2 amount is more, so the ratio is high. So again, from the gas profiles, you can understand that one. Again, you can look at, you know, what kind of methanotrophs that are there in different columns and how they are changing. See the, you know, before incubation, and then phase 1, we do again phase 2, phase 3. So in each situation, we know how much is the oxidation and what is the type of methanotrophs that we have. So look at it, you know, in this situation before incubation, we have a very less amount of methanotrophs, but after that, you know, after phase 1, you can see significant amounts of methanotrophs that are generated in the system. So we can, you know, this is the phase 2 in the setup, and then we can again look at the microbial characterization at different phases, and is there any shift in the microbial population with the different phases that we are doing. So the publication, you can look at, you know, you will get tremendous amount of data. Sometimes interpretation of this data becomes a bit challenging. So then, you know, we put this, you know, we looked at, we put a biochar amended soil on the top of the distribution layer. Now we want to put a slag on the top of it. But that's our real hypothesis, right? We want to have a biochar amended soil, and on the top of it, we want to have a slag. And we added sand in between them just so that we can collect the sample. You know, what is the gas composition that is coming from the biochar amended soil, and that is entering into the BOF slag. So here are the pictures. You can look at, you know, how we are mixing it and how we are placing these columns, and then, you know, sampling and gas analysis pictures are also shown here. Again, we do this testing in different phases: phase 1, phase 2, phase 3, phase 4. Again, we are varying, you know, the flux or the flow rate and the duration to understand, you know, variable inflow conditions in a scenario. Interesting things, you know, let's look at the column 1. You see, you have high concentrations of methane and CO2 throughout the column, and you can see even the concentrations at the top. But if you look at the column 3, you can see that CO2 concentrations are higher at the bottom, but as it comes into the slag layer, you can see the concentrations are reducing significantly, and near the top you have 0 concentration. That means completely CO2 has been sequestered. Even methane, you know, concentrations have been decreased significantly, and you have very minimal emissions on the top. So these columns again revealing that CO2 can be sequestered by slag, and then methane is converted into CO2 by the biochar amended soil. So I can show, you know, a lot of data on what we did in terms of the microbial characterization. We looked at whether we have a type 1 methanotrophs, type 2 methanotrophs under certain conditions. Type 2 methanotrophs, presence of that led to higher methane oxidation. And then we looked at H2S removal, and we found out that H2S was not really transported into the biochar amended soil or into the slag. You know, most of that was sequestered by the gravel itself, and that really made us think, okay, what kind of a distribution layer we need to use. So we tested the gravel, we tested the field sand, we tested the clean sand, and we said the control, you know, there's nothing, no change. But if I use the gravel, like here, you see the H2S decreasing just by the gravel itself. So that's what, and then we realized that field sand is also not good. And then we realized that clean sand is the one that we should be using if we don't want this H2S to be sequestered here and maybe it should then it will go into the system, the layer above it. So the bottom line is, that should help, or even if that gravel layer is doing the job, that's good. And we did not other experiments where, okay, we got optimized biochar amended soil layer and BOF slag. Can we compare side by side, conventional soil cover system versus our biogeochemical cover system? So we set up these two columns. We wanted to compare side by side. Again, we prepared all these things, the materials, and looking at, see the column, how we are going to place it in there, and kind of shows you the procedure for preparing these columns. I'm not going to talk about these results, but then after doing these things, again, we verified that biogeochemical cover system is working well. And then we went into doing in the large column test. Actually, we were supposed to go out to the field and do some test plots, but because of the COVID situation, we could not do that one. So basically, instead of going out to the field, we tried to create a large scale setup in the lab and say consider that one as the field test plot, because we had to do we cannot wait until we go to the field, and that was a very uncertain thing. So what we had was biogeochemical cover, biochar amended soil, on the top of it is BOF slag, and then you have on the top is the vegetative soil, and then soil cover, again, just a cover soil, drainage sand, and topsoil. Okay, and the good thing here is BOF slag, it is permeability is as close to the sand as possible. So this serves the dual function. It serves as the drainage layer. It also serves as the carbon CO2 and H2S sequestration layer. So this is the conventional soil cover, and this is our alternative biogeochemical cover systems. So we wanted to test it in a large tanks. So this is the schematic of the large tanks. And then I want to show you the pictures of this, how this looks like. So this is how, the schematic. So you have a biocover layer, basically biochar amended soil layer, and the drainage layer or a slag layer, and then you have a topsoil here. And then what we do is we inject the gas from the bottom, and then we have the probes, gas probes, that give us the concentrations at different depths in different layers. And then at the top, we can open this to simulate the atmospheric conditions during the normally. But if you want to measure the gas emissions, we close this one tightly, and then the collected gases can be sampled. So we have the gas sampling here and the gas sampling at different ports. So that will give us an idea how much of gases are removed. So this is very tedious task. These tanks are really large, and all the work that I'm showing here is done by Jyoti. She just graduated last year. She's working in a consulting company right now. She did an amazing job. You think the girls cannot do the hard work. She proved it to be wrong. So he went to the landfill site. We got the soil. Lots of buckets of soils that we got, and then a lot of mixing and homogenizing it, and then mixing the soil with the biochar, and then placement into these tanks here, and these two tanks. So one is the soil cover, other one is the biogeochemical cover system. So we have the gas probes on the top. Where whenever we want, we can open up the top and then collect the gas samples. When we want to see the outflow flux, so we seal this one, we have that outlet, and then we measure the gas coming out from there. So you can measure basically this is called static chamber method that can be used in the field. So these are the probes that have gone to different depths, and that gives you the concentration. So this is all the details about testing. So here she is. Jyoti is trying to prepare a sample. So here is the big tank that you can see, compare with her height. So it's really, really tall, and it's a stainless steel, heavy. And then see here, she placed a layer of the soil and she's so excited about it. And here is another column. She's done. She's so excited about getting this thing done. Most of the work was done by herself. And of course, Gaurav is another student. He is pursuing PhD, continuing this project. He joined her towards the end, and he was helping her in this preparation of the samples. And the columns are all set up. Everything is ready to go. Test started, and she is very happy. And I think, our research is going to be excellent if we have very dedicated, very curious, very enthusiastic researchers like Jyoti. So here are the materials that we used. We had biochar amended soil, biochar, slag. Of course, whatever the materials that we used, they were characterized first. And then we had characterization of mixed soils also. And then we did some testing. Um, and we basically found out that biochar amended soil during the phase 1. You see the biochar amended phase 1 is the methane oxidation removal efficiency compared to the sand layer here. And then just looking at even the surface emissions, the biochar amended soil was not emitting any surface emissions, whereas soil cover was emitting emissions. And then CO2 emissions, biochar amended soil had 0 emissions, and soil cover has some emissions. So these are the very preliminary results, and then we continued the testing for a longer period and the different phases. My current student Gaurav is analyzing the results from different phases. But the initial results showed that biogeochemical cover system can reduce the methane emissions, completely eliminate the CO2. So our goal was to completely eliminate it, but we could get some amounts of gas emissions, but significantly decreases the emissions. So here is our final thought, what we are trying to recommend: biogeochemical cover system versus conventional cover system. Now the question is, okay, will it reduce the infiltration? How much it can trap the methane, and what is the slope stability, because we're going to use on the slopes. We did all this analysis, infiltration analysis. We showed that biogeochemical cover system can reduce the infiltration. Okay, so and the methane emissions can be reduced by BGCC. So that means it serves the dual purpose, infiltration reduction and also methane emission mitigation. And then slope stability, if you have used on the some of the cover should be on the side slope, right? In the top, that's okay, that's flat or slight slope, but in the side slopes, we wanted to see if stable. And we did a life cycle assessment to see if it is sustainable. Or this is the life cycle inventory and impact assessment that we did, and we showed that BGCC, that biogeochemical cover system is highly sustainable, environmentally sustainable. Actually, it uptakes, is a negative, carbon negative. So it actually takes out the carbon rather than emitting the carbon. So overall, we found out that based on this life cycle assessment, our biogeochemical cover system is highly environmentally sustainable. So and we able to document that in this one. And we did also sensitivity analysis to see, hey, do we get how far what is the distance of these materials being available? And we did that analysis. And of course, when you're using the materials from sustainability point of view, those materials should be available close to the site. If you have a lot of transportation, then the material may be cheap or no, does not cost, but the emissions due to transport will be will make your project not environmentally sustainable. So that's why, you need to think about it, using the waste materials in any application, that's not as sustainable. You cannot, generalize that, you are doing a sustainable, but doing the project towards the sustainability. You really, if the materials and the byproducts or waste materials, if they're available close to the project site, then you can say that one, because the distances can make, it's probably easier to use the virgin materials, the conventional materials, if they are available close by, rather than getting these waste materials from far off distances. So the final comments is biogeochemical cover system. Based on our extensive research, we find out that they can mitigate methane, CO2, and H2S close to zero emissions, and it's practical and resilient to wide range of climate conditions. I didn't show you the results, but we did the testing, batch testing under different temperature conditions and different moisture conditions, so to simulate flooding conditions versus drying conditions. So we were able to find that this methane oxidation and carbon sequestration can happen under different temperature and moisture conditions that simulate the varying climate conditions. So basically, we're using the waste materials. Biochar is a byproduct of biomass gasification. BOF slag is a byproduct of steel manufacturing. Right now, the uses of these are less, and we can, use these things instead of, putting them in the landfills or creating the stockpiles, and the resource conservation. If we didn't use this one, we would have used natural materials. And is it economical? As I said, it will be economical if you don't have too much transport distances. Is that sustainable? We demonstrated that it is sustainable. And another important thing that I could say is it could have a broader applications, adaptation to address even toxic emissions that could be emitted at dumps and contaminated sites. So if you don't want to emit greenhouse gases or toxic gases into the atmosphere and affecting the climate change and public health, maybe just throw a layer of biochar amended soil or just a layer of biochar, and then on the top of it, throw a layer of slag, and you will reduce the gas emissions substantially. Again, I want to thank all the work that I presented. Most of it is done by Jyoti for her PhD. I want to thank her for doing an excellent job. So here is my contact information. I already gave you the link in the chat box, so you should be able to find the publication that I mentioned. Okay, so with that one, I can take any questions that you have. I hope the presentation was useful in terms of creating a solution to the gas emissions at dump sites or landfill sites.
Thank you so much, sir. It was a very extensive and very detailed presentation.
Thank
I
you.
mean, there's a lot of work going on. I think it will be great for all the participants and especially myself actually to see everything, in one end of our lecture. Thank you so much. So now we can have any kind of discussion, Q&A session.
We have about 15 minutes to, spend. So just like yesterday, again, people needed a little bit of push to ask questions. So just say, let us give 1 minute for people to think about what they want to ask. Again, I want to see your presence. Like yesterday I mentioned, I want to see if you're listening or just logged in and doing something else. So any comments or questions? Everyone.
So somebody requested in the group, sir, to share a kind of Google form for questions because they could not, have it, and maybe some of them were interested to see the recordings of the previous days, and then they can discuss that on the next day.
Yeah,
So
yeah.
recordings I could not provide, but Google Form has been shared by Nikhil to all the participants. So you can even post it, like, whatever you have it. And there is a specific mention there, like if you want to have a specific discussion with a specific speaker also, you can put it up there. So I want all the participants to use that, and then so that we can have in the last day, we can have a more detailed session also.
So yeah, Swati, can you put your question to everyone so that everybody can see your question? Could you please, you are sending that question to me. Instead of that, can you post it to everyone? So, and think about everyone asking me some questions. So, my question is, why the USA has no waste to energy treatment plant? What they do with the paper waste? So, a lot of organic waste is composted, and then waste to energy plants are not common because in the past, waste to energy plants were there, and they didn't have good emission control systems, and then with the dioxins and everything else that is emitted, surrounding people had cancer, and there are a lot of public opposition for the waste to energy plants, and regulations I think require incinerators or waste to energy plants to demonstrate through modeling that there will not be any impact by their plants around certain radius. So, and demonstrating that one is very, very challenging, like through air dispersion modeling and everything else, and then all the modeling assumptions that you have to do. It's never justified. I mean, you will never win against the environmentalists. So that's why we have a very few plants that have been that are being shut down one after the other. So we don't have waste to energy plants. But situation is different in Europe, right? Europe has a lot of waste to energy plants. They have a very strict controls on the emissions. So they have a technology to use that one, right? And the reason is that they don't have a land. In US, we have a lot of land. And it is a cheaper option or cheaper or more environmentally friendly option is to build these landfills far away. These are like a mega landfills away from the cities, and then use that one for waste disposal rather than having the waste to energy plants. If I made it correctly. Swati sent me a question directly. Is fly ash can be used in landfill covers to mitigate landfill gas alternatives to biochar? So we are, the other question, I mean, we are looking at it. My student is looking at it. So if I say biochar amended soil and slag, okay, if they're not available, what can I use? So what are the other local materials that are available that can be used? So we are trying to come up with alternatives to slag, alternatives to biochar. Yeah, you think about what are the available materials and see what kind of properties that you need um, for the material that you want to use it. Biochar amended soil has to have a low permeability to allow less infiltration, and then the slag layer has to be more permeable. So yeah, definitely to make it sustainable, you need to for us it's kind of easy, like biochar is the one that can be it's a little bit tricky. If you have a commercial plant close by, you can use it. If not, these landfill owners can have their on-site plant and accept that organic waste and then create the biomass, um, create the biochar. But if biochar is not available close by, then that's not a good option. So you need to find out what are the materials that are available close by. Can they serve similar to what I showed in for as a biochar amended soil or for the slag? And we are looking at different alternatives to the slag and the biochar. Biomining, is it more helpful? Okay, wonderful. Okay. Our corporation doing my biomining, is it more helpful? I think, the biomining, I don't really understand the whole concept of it. Of course, people argue that these legacy wastes have been there for a long, long time. All the biomass, all the organics is degraded. There's not much there. Just a little bit of conditioning is needed. And then basically most of the biomining that's going on right now, and they say that even I visited a biomining site near Chennai, and they showed me like, some of the culture that they use. We asked them the questions about like, do you have research data that shows that how this can degrade the waste? There's not much information about that. So basically, it's more of a separation of the different fractions, and which is okay. The legacy waste, and if it's all degraded, and you're separating up the inorganic fractions and trying to utilize those inorganic fractions for different purposes, that's fine. But the problem that I have is at the legacy waste, if you are not accepting the new waste, then you can think of one day, these legacy dumps going away, right? But the problem is they are doing something, biomining, processing it, but on the other hand, they are getting the new waste. So how can you, do the material balance? You cannot really make this dumps disappear if you're continuously getting the waste. Okay, any other questions? I know yesterday I asked, if anybody is a faculty members. I saw a bunch of you are working as faculty members. I think you could undertake some projects similar to this one, or you could have some ideas based on my presentation, and then you can have students to do some projects. It could be, master's level, it could be PhD level, even it could be undergraduate level. If they are doing some capstone project or undergraduate project, BTech project, you can have them, explore some of the ideas that you got through my presentations.
Good evening, Professor Krishna, sir.
Gangadhar, how are you, sir? You are there.
Yes, sir, I am there, sir. How are you doing, sir?
Very good, very good.
Actually, sir, I have few doubts and not doubts exactly. So I want some guidance. So because some of my students are working on fly ash and on as well as expansive soils, we are using two kind of biomaterials like biochar and biopolymers. So till now we succeeded somehow, like we got better results in terms of permeability, consolidation, and some of the engineering properties. But due to lack of experiments here and any facilities, so I could not go further little bit into the utilization of this material as a landfill liner. So could you please throw some light on it? So how can I proceed using these expansive soils? Like we got better reduction of swelling and shrinkage values, and moreover we are not getting any kind of high shrinkage levels. So I know like if at all we are using it as a kind of bottom liner material, so I don't think there is a issue with swelling and shrinkage. So can I use this stabilized material as a landfill cover?
Yeah, it's actually the another advantage. I didn't highlight that one. So using the biochar, you can reduce the shrinkage and swelling. The reason is, the biochar absorbs the water and makes it available. So even in our column experiments, we could see if you have just the soil, you will see a little bit of drying and cracking. Whereas, if you add a biochar, it doesn't have to be expansive soil, even regular soil with with the drying, you could see the micro cracks in the soil cover, but when you have a biochar, you don't see those micro cracks. So it has that advantage also. So, and expansive soil, it could reduce the swelling. But, we need to think about, the effect of that one on hydraulic conductivity. So definitely it has a lot of positive impacts on that one. So the biopolymers is a good option, but like you need to think about degradability of that, and then using the mass amounts of biopolymer that you need. Even when you're talking about the landfills, you're not talking about small area. You're talking about, let's say, 100 acres, right? 100 acres of like 2 feet of soil. You can calculate how much biopolymer you need. So
Yeah,
100
but
acres, 100 acres of
yes, sir. Based on our
100 acres.
preliminary studies, I found most of the studies are even when I was in my postdoc at China. So we used to recommend like 5%, 10% of biochars. So for
The
any kind of
biochar should be good. Biochar is like a waste material, right? I mean, you can produce it at on-site. You can use any, biomass, any invasive, non-invasive, invasive species, any junk that you can find. You can, in China, they created biochar with cat litter, right? Cat litter, or, poultry litter,
water
any, yeah, anything. But that's easy. Like, you can burn it and then create it and then use it. But the biopolymers, right? You need to that's like a processed chemical. How much of that you need it, and how you can apply on a large scale. It's like a huge amount of science. I mean, as I said, like biochar would be much more feasible than biopolymer, in my opinion. And the cost wise also, it's much cheaper to get a biochar versus biochar. If you have a biofuel plant, you're getting that one as the process, right? I mean, also it does not need any energy. It could be a net negative energy process. The energy that is generated, is looped into pyrolysis process. So overall, that could be better option. So that's why, you know, uh, yeah, even for that landfill cover, the more is better. But when you say 10%, the quantity of the biochar you need is a lot more. The quantity of the soil that you're talking is large. So that's why we started working with a 2%, 2%, 4%, 6%. And then sometimes, we don't have luxury of varying that percentages at smaller increments. So hey, if it happens in 10% to the maximum extent, maybe we can reduce it a little bit level. So further optimization of the biochar content is needed. And then
yes, sir. Actually,
all
based
biochar.
on our
Pardon me. Go ahead.
yes, sir. Yes, sir. Please continue.
No, I'm saying also all biochars are not the same. So again, you have to be careful. Whatever the test that you have done with your biochar, maybe if you use a different biochar, will you get the same results? So that's another important thing, in terms of the variability of the biochars.
Okay, sir. Just in terms of percentage, you were saying like 8 or 10% or 5% of biochar, but we got better results like in terms of strength or in terms of permeability, like for 0.5% or 1% of biopolymers, sir, like Janathan Gum or Gaur Gum. So even we were one of the paper co-authors. So when I was my PhD work, so you might have seen some of the results, like we used to remediate dispersion studies just using 0.5 or 1% of biopolymers. So like as far as my knowledge, like I have done some kind of economical study, but it is very expensive at this point of time. But I'm not sure like how the process can be reduced or so that we can have better economical process and other things.
No, you have to look at the
So
application, right? So
yeah,
the application, for example, it's a roadway project. You are looking at a small stretch of the roadway. That's different than 100 acres of landfill with 2 feet of soil. That's, the magnitude of the material is different. So yeah, biopolymers has applications. For example, we use it even in slurry walls and other places. So I'm saying, just we need to look at how much quantity we need it, and does it make sense to use that much quantity? Right?
Okay. Thank you, sir. Just I got some couple of good results, sir. So in a couple of days, I will come back to you. So by
Sure.
email.
Sure.
So we will come and get further.
Sure. Sounds good. Keep doing the research.
Thank you, sir.
Sure.
So a few more questions are there in the chat box. Can this biochar be used in soil contaminated by hazardous waste and electronic waste as well?
Yeah, what is the biochar in landfill covers? What is that? Contamination can be used for contamination? Where is that question? Okay. So can biochar increase the crop production, or it just increasing the carbon content? Yeah. So it actually increases the crop production. So there's a paper that I wrote. You can look at it, and so that's why farmers like using the biochar very much, because it has a high moisture retention capacity, and it also has high nutrient retention capacity. Because of that, people have done simultaneous test plots and grew crops, and they clearly showed that biochar amended soil will yield high crop productivity. What is the life of the biochar in landfill covers in the field? What is the ideal percentage of biochar to? So the biochar can last forever. That's kind of the advantage of that compared to other organic amendments. As I said, compost could degrade it, but biochar is very stable carbon. Ideal percentage of biochar, that's what we have been discussing it. The lower the better, but you need to optimize that one based on the soil you're mixing with, and also the gas flow conditions that you're going to have. So the maximum we used is 10%, but if you can minimize that percentage to 2% to 3% or 4%, that's why I think one of in our field test, we try to see, instead of mixing with the soil, can we just put a thin layer of biochar? So as the gas comes up, maybe that thin layer of biochar, if a methanotrophs acclimate, it's kind of the bio layer, but that didn't really work that well. So we need to amend the soil with the biochar, and the smaller the amount, the better it is. So that okay, does the strength of the biochar amended soil play important role when placed in landfill as cover soil? Because for some biochars we get high strength, but for some other feedstocks the strength may be reduced. Yeah, so the strength may be important because you have to consider the strength. You are putting on the landfill slopes, right? The slope stability is important. So you have interface stability, but the stability of the material by itself. So you need to have a good shear strength. And yeah, depending upon that's why I in my slide I said all biochars are not the same. So the biochars can be behaved quite different. We use the biochar for everything in general, but that are produced by pyrolysis or gasification of a biomass. So what is the biomass that you're using? And the pyrolysis process or gasification process, what is the temperature that you're using? What is the residence time that you're using? So you could be using the same feedstock, but if the temperature is different, you get a different biochar. And if residence time is different, same temperature, but residence time is increased, then you're going to get different biochar. So it's like, the pro and cons. So basically, the advantage of this is you can engineer biochar to meet your needs. That's kind of the beauty of this. You can take the feedstock, or you can control the feedstock. You can control the pyrolysis process to produce the biochar that of the properties that you want. So there are infinite opportunities to engineer. And moreover, I didn't talk about this one. I talked about activated biochar, but there are many other ways you can modify the biochar to get the results that get the properties that you want. So there's a you can see, they add different types of um, um, amendments to uh, change the properties of the biochar, or better make them better. That's Bhumi, right? So Bhumi, can you explain your research a little bit? Somebody was asking about for the biochar for remediation purposes.
Yes, sir. Good evening, sir.
Good evening. Good evening.
I'm PhD student at SPNIT Surat, and I'm working on remediation of lead contaminated soil using moringa seed biochar. So whatever moringa seed waste is collected, like we have oil seeds. So after the extraction of the oil from the seeds, there is a cake that is formed. That is a waste. So I've used that waste to convert it into biochar using pyrolysis, slow pyrolysis, and I have used it in remediation of lead contaminated soil. So yes, we can use biochar for
Okay. Somebody is asking, Bhumi, what is the temperature that you've used for the pyrolysis?
I have used 350 degrees Celsius.
350 degrees Celsius. The reason I am asking Bhumi is I'm helping her out. I'm learning from her some of the testing that she has done, and so that's why I know her work. Okay, any other questions? The one important thing that you have to remember when you talk about biochar. So a lot of research is done on biochar that is made in the lab. Some people take some biomass and then use the lab pyrolysis unit and make it. Then the question that you have to ask is, you need to be able to produce the same biochar quality in a large scale in field scenario. You should always think about field application. So yeah, in the lab you can make 250 grams of biochar with a simple pyrolysis lab unit, and then you can do all the testing with that one. You find all the results. But then if I want to use it out in the field, I need large quantities of the biochar. Can you scale up your pyrolysis unit for that? So what we did is, hey, we didn't want to create a biochar. So we looked at how are the vendors, who are the commercially producing, because if I'm using the landfill liner for the covers, I need large quantities of the biochar. So are there somebody who can provide it? Yeah, we found out there are a bunch of commercial biochar producers. So what we did is we got the biochar from those producers, and then we tested that one in our lab. So then the question is, how do you know that that guy or that manufacturer is going to produce the same quality biochar, every time that you need it, right? So the whole idea of us was to create, the specifications for the biochar, what kind of properties that biochar should have in terms of the gradation, in terms of the water absorption capacity, basically you need the specifications of the biochar. And it doesn't matter, whatever the way that, however they want to manufacture when I get the material, when I get the biochar should meet my specifications. So the specification, or performance specification-based biochar is the way to go forward, because you cannot control the biochar production in a large scale. Sometimes you have a better control, sometimes you don't have any control, but you leave up to the manufacturer, but to say whatever you do it, but the end product has to meet these specifications. So as an engineer, that's what we can do it. You are not in the business of manufacturing the or preparing the biochar. Sounds good. I think we have taken 15 minutes more than our regular time. Professor Nilima, you want to wrap it up?
Sure, sir. Yeah, sure, sir. Okay, so thanks so much again. And thanks to all the participants for active discussions. So again, we'll see you tomorrow at 4:30. Thank you all.
Thank you.
Still, if you have any, you can put your questions in the feedback.
Okay, thank you, everyone.
Thank you, sir. Thank you. Good night.
Thank
Good night,
you.
ma'am. Shall we end the meeting from host side? May I end it?
Yeah.
Okay,
Thanks, everyone. Thank you.